Oreos, Pringles, and Nerds all hide a secret in the way they are made. Oreos are baked and filled so the cookie can split cleanly. Pringles are pressed from potato dough into identical curved crisps, and Nerds are built by coating tiny sugar crystals until they become colorful candy. In this video, we uncover how 3 snacks get their signature shape before they reach the shelf. Oreo cookies become unmistakably recognizable at the exact moment a thick ribbon of white creme lands between 2 perfectly embossed chocolate wafers, but by then, nearly every complicated step has already happened. The sandwiching machine works with astonishing precision, placing identical portions of creme onto thousands of moving cookies every minute before another wafer settles gently on top. In only a fraction of a second, 2 separate products become one. The finished cookie now looks complete, yet another series of carefully synchronized operations still waits ahead before a single package leaves the factory. To understand how those perfectly aligned cookies arrive at this point, the process has to rewind to where nothing resembles an Oreo at all. Long before the creme is mixed or the wafers are baked, dry ingredients begin arriving through completely separate handling systems. Flour travels pneumatically from bulk storage silos into enclosed weighing hoppers, while sugar, cocoa powder, salt, leavening agents, and other dry ingredients follow dedicated transfer lines of their own. Every ingredient is metered with remarkable accuracy because even small variations influence the finished wafer's texture, expansion, and strength. One by one, they enter enormous industrial mixers, where rotating paddles begin blending thousands of kilograms of material into a completely uniform dry mixture before liquid ingredients are introduced. Water and liquid oils enter gradually while the mixers continue turning. At first, the ingredients resemble coarse crumbs tumbling around the bowl. With every revolution, however, the particles absorb moisture and begin binding together. The once loose mixture transforms into a dense chocolate-colored dough that grows smoother and more cohesive as mixing continues. Unlike bread dough, this mixture is not developed to create a strong gluten network. Instead, the objective is to produce a dough that can flow consistently through forming equipment while baking into a crisp, delicate wafer rather than a soft bread-like texture. The mixes continue only until every ingredient has dispersed evenly throughout the batch, after which the dough moves toward the next stage almost immediately. Instead of heading straight into an oven, the dough first passes through feeding systems that deliver it onto large, sheeting rollers. Heavy rollers compress the dough into broad, continuous sheets while maintaining consistent thickness across the entire width of the production line. Every adjustment matters because uneven thickness would produce cookies that bake differently from one another. Laser measuring systems continuously monitor the sheet, while automated controls make microscopic corrections to roller spacing, ensuring the dough remains remarkably uniform before shaping begins. Now comes one of the most recognizable stages in the entire process. Rotary molding cylinders engraved with the familiar Oreo design rotate against the moving dough sheet. As the patterned molds press downward, they simultaneously cut each wafer into shape while imprinting the decorative surface that has become instantly recognizable around the world. The detailed floral pattern, geometric border, and raised lettering all appear during this single operation. Excess dough surrounding the freshly molded wafers separates cleanly before conveyors return it to controlled recycling systems, where it blends with fresh dough in carefully regulated proportions. Meanwhile, the perfectly formed wafers continue forward in endless rows, already displaying their final appearance despite still being completely raw. Although the cookies now look finished, their greatest transformation is only beginning. The freshly molded wafers enter an exceptionally long tunnel oven divided into multiple heating zones. At first, gentle heat begins warming the dough, while moisture inside starts migrating toward the surface. As the conveyor advances deeper into the oven, temperatures rise steadily. Water trapped throughout the dough converts into steam, expanding tiny internal spaces while leavening agents release gases that help establish the wafer's final texture. Starches gelatinize, proteins solidify, and sugars participate in browning reactions that deepen both color and flavor. The once soft dough gradually hardens into a crisp chocolate biscuit capable of supporting the creme filling that will arrive later. Inside the oven, airflow is just as important as temperature. Carefully directed streams of heated air circulate around every wafer, promoting even baking from edge to center. Conveyor speed determines precisely how long each cookie remains inside every heating zone. If the wafers move too quickly, excess moisture remains trapped inside, leaving them too soft. If they remain too long, unnecessary moisture loss can make them overly fragile. Every second contributes to achieving the familiar snap that defines a properly baked Oreo wafer. As the cookies leave the oven, they remain surprisingly delicate despite their crisp appearance. Internal heat continues moving outward, while moisture redistribution slowly stabilizes the structure. Long cooling conveyors now take over, stretching across significant sections of the production hall. Ambient and conditioned air circulate gently around every wafer, while conveyors provide enough travel time for temperatures to fall gradually. Cooling too quickly could create unwanted stress within the biscuit, while insufficient cooling would soften the creme applied later. This quiet stage receives little attention compared with baking, yet it determines whether the next operation succeeds. While the wafers cool, another production line has been operating independently. Inside massive stainless steel mixers, the signature Oreo creme filling begins taking shape. Sugar enters first, followed by vegetable fats and additional ingredients that create the filling's smooth texture and bright white appearance. Powerful mixing blades fold and whip the ingredients together continuously. At first, the mixture appears heavy and dense, but as mixing progresses, it becomes lighter, smoother, and remarkably uniform. Tiny air pockets distribute throughout the creme, while its consistency changes into a texture soft enough to deposit accurately, yet firm enough to hold its shape between the cookies. The finished creme enters insulated holding systems equipped with slow-moving agitators that prevent separation while maintaining ideal depositing consistency. Pumps transfer the filling through enclosed stainless steel piping toward the sandwiching machine. At this point, two entirely separate production streams, freshly cooled wafers and freshly prepared creme, are finally approaching one another. The sandwiching machine operates with extraordinary synchronization. Bottom wafers travel along precisely spaced conveyor lanes, while depositing nozzles release measured portions of creme directly onto their centers. Every deposit matches the next in both weight and position. Immediately afterward, another conveyor carrying top wafers aligns perfectly above the first. Mechanical guides lower each top wafer gently onto the waiting creme, before carefully controlled pressure compresses the sandwich just enough to spread the filling evenly without forcing it beyond the cookie edges. In an instant, thousands of individual components become complete Oreo cookies. Now another challenge begins. Although the cookies appear finished, the freshly deposited creme still requires time to stabilize. Conveyors carry the assembled cookies through conditioning areas where temperature remains carefully controlled. During this stage, the filling firms gradually while bonding securely to both chocolate wafers. The cookies become much more resistant to movement, preparing them for the rapid handling systems that follow. Sophisticated inspection equipment now evaluates every cookie moving along the conveyor. High-speed vision cameras examine wafer alignment, embossed pattern quality, creme position, overall diameter, color consistency, and visible defects. Sensors also monitor cookie height, ensuring the creme layer remains within program tolerances. Any cookie with broken wafers, incomplete filling, poor alignment, or other detectable irregularities is removed automatically without interrupting production. Only properly assembled cookies continue toward packaging. Before entering retail packages, the cookies must first be organized. Individual conveyor lanes merge into carefully controlled groupings where guide rails align every cookie vertically. Stacking mechanisms begin building precise columns by lifting and lowering cookies into predetermined counts. Timing throughout this section is exceptionally important because every retail package requires exactly the correct number of cookies arranged in the proper orientation. Mechanical fingers, synchronized conveyors, and optical sensors work together continuously to maintain uninterrupted flow even at remarkably high production speeds. Pringles emerge from a towering stack inside their iconic can, looking perfectly identical, but every crisp in that column has already survived an astonishing sequence of grinding, mixing, rolling, cutting, frying, seasoning, and precision stacking before the lid ever snaps into place. The packaging line may appear to be the end of the journey, yet it quietly reveals one of the biggest engineering challenges in the entire factory. Every crisp must arrive with exactly the same curved shape, thickness, and strength. If even a handful vary slightly, the stack becomes unstable, the crisps chip, and the entire can loses the uniform appearance that defines Pringles. Long before the first can is filled, every stage of production works toward achieving that remarkable consistency, and the process begins by transforming simple dry ingredients into something that hardly resembles a potato chip at all. Unlike traditional potato chips sliced directly from whole potatoes, Pringles begin with a carefully prepared dry blend. Potato flakes form the foundation, arriving from dedicated storage systems where moisture and temperature remain tightly controlled. Alongside them come potato starch, corn flour, rice flour, wheat starch, salt, and precisely measured functional ingredients that influence texture, flexibility, and expansion during cooking. Each ingredient follows its own enclosed transfer system toward automated weighing stations where every quantity is measured according to tightly controlled production specifications. Once the correct proportions have been verified, the ingredients enter massive industrial mixers that begin combining them into a completely uniform dry mixture. At first, the blend resembles a pale powder flowing freely through the rotating mixer, but another transformation is already approaching. Water enters gradually through carefully positioned spray nozzles while the mixers continue turning. Rather than flooding the ingredients all at once, moisture distributes evenly throughout the dry blend, allowing countless tiny particles to hydrate at nearly the same rate. The mixture begins forming small clumps before gradually developing into a smooth, cohesive dough. Powerful mixing paddles fold, compress, and stretch the mass repeatedly until every portion reaches the same consistency. Unlike bread dough, the objective here is not to create a highly elastic structure, but a smooth, workable sheet that can pass through rollers without cracking while still producing the delicate crispness associated with the finished product. By the time mixing ends, the once powdered ingredients have become a dense, pale dough, completely different from the materials that entered only minutes earlier. Instead of moving directly toward cooking, the dough first enters a conditioning stage. Large holding systems allow moisture to distribute evenly throughout the mixture, eliminating dry pockets and ensuring every section behaves identically during rolling. Although the dough appears motionless from the outside, microscopic changes continue throughout its structure as hydration reaches equilibrium. This quiet step often goes unnoticed, yet it plays a major role in producing sheets that remain smooth and uniform under the enormous pressures waiting ahead. The conditioned dough now approaches one of the most visually striking sections of the factory. Heavy sheeting rollers begin compressing the dough into an increasingly thin, continuous ribbon. Each successive roller reduces thickness slightly, preventing sudden stress that could tear or distort the sheet. Laser measurement systems monitor thickness continuously, while automated controls adjust roller spacing in real time. What started as a dense mass now stretches into an endless blanket of dough, traveling steadily across wide stainless steel conveyors. It still looks nothing like a finished Pringles crisp, but the next machine changes that almost instantly. Rotary cutters descend rhythmically onto the moving sheet, punching out perfectly round discs with extraordinary speed. Every circular piece matches the next in diameter, while the surrounding excess dough separates cleanly and travels back toward controlled recycling systems, where it rejoins fresh dough in carefully regulated proportions. The newly cut discs continue forward independently, their edges remarkably smooth and consistent. Although they now possess the familiar circular outline, they remain completely flat. The signature saddle-shaped curve that allows Pringles to stack so precisely has not appeared yet. That transformation waits only a few meters ahead. Each flat disc enters a specially engineered molding system where opposing curved molds gently capture the dough as conveyors continue moving. Controlled pressure forms every disc into the distinctive hyperbolic paraboloid shape recognized instantly around the world. The forming process lasts only moments, yet it permanently changes the geometry of the crisp. This curved profile is far more than a design feature. It increases structural strength, helps distribute seasoning evenly, allows efficient stacking, and gives every crisp the mechanical rigidity needed to survive packaging with minimal breakage. Without this precisely engineered shape, the iconic Pringles would never function the way it does. Now the formed dough finally approaches the stage where texture changes forever. The molded pieces transfer smoothly into continuous frying equipment filled with carefully controlled cooking oil. As each crisp enters the hot oil, tiny bubbles immediately begin racing across its surface. Moisture trapped inside the dough converts rapidly into steam, escaping through countless microscopic pathways while leaving behind an increasingly crisp structure. The outer surface firms, first before heat gradually penetrates toward the center. Conveyor speed determines exactly how long every crisp remains submerged, while temperature sensors continuously monitor the frying oil to maintain remarkably stable cooking conditions throughout the production run. As the crisps leave the fryer, they already display their familiar golden appearance. Yet another important transformation is still taking place. Excess oil clinging to the surface must be removed without damaging the delicate structure. Vibrating conveyors and precisely directed air systems encourage excess oil to drain away while maintaining the crisps in their carefully molded orientation. Every adjustment influences the final texture. Too much retained oil alters mouthfeel, while too little changes flavor delivery during seasoning. This balancing act prepares the crisps perfectly for what comes next. The seasoning stage arrives almost immediately after frying because the surface remains slightly warm, helping dry flavor particles adhere more effectively. Rotating seasoning drums receive the freshly cooked crisps in continuous streams. As the drums turn gently, carefully metered seasoning blends enter through precision dispensing equipment positioned above the moving product. Fine particles of cheese flavor, sour cream, and onion seasoning, barbecue spices, paprika, salt, vinegar powders, or countless other formulations drift downward in controlled clouds before coating every exposed surface. The rotating motion continuously lifts and redistributes the crisps, ensuring remarkably even coverage without excessive breakage. Hidden inside the seasoning systems, computerized controls monitor dispensing rates continuously, so every batch maintains consistent flavor intensity from the first crisp to the last. By now, the crisps finally resemble the finished product, but they are still traveling individually. The next section of the factory performs one of the most impressive mechanical operations in snack manufacturing. Instead of allowing the crisps to pile randomly into bags like many other snack foods, automated orientation systems begin aligning them into perfectly organized stacks. Carefully designed conveyors guide every crisp into the same direction, while mechanical channels gradually gather them into neat columns. Sensors monitor stack height continuously, ensuring each column contains exactly the programmed number of crisps before moving forward. Watching hundreds of perfectly formed stacks travel side by side creates the unmistakable image associated with Pringles production. Meanwhile, the iconic composite cans begin their own independent journey. Flat paperboard material has already been wound into rigid cylindrical bodies before receiving the familiar printed graphics. Metal bases attach securely to one end, while empty cans travel upright along dedicated conveyors toward the filling area. Plastic lids and protective foil seals wait nearby, prepared for the final stages of packaging. Until this moment, the cans and the crisp stacks have remained completely separate. Now their paths finally intersect. Mechanical loading systems gently transfer every completed stack into an empty can from above. Rather than dropping loosely, the stacks slide downward in one smooth movement, preserving their careful alignment all the way to the bottom. Because every crisp shares exactly the same curved geometry and dimensions, the stack fits snugly inside the cylinder with remarkably little wasted space. This precise fit not only protects the product during transportation, but also allows consumers to remove the crisps one after another with minimal breakage. Immediately after filling, each can move towards sealing equipment. A foil membrane positions itself across the opening before heat sealing equipment bonds it securely to the rim. This protective barrier helps preserve freshness while creating the familiar seal removed by consumers before opening. Plastic overcaps then descend automatically from orienting systems before pressing firmly onto the top of every can. The package now becomes completely enclosed, protecting the crisps from moisture and physical damage. Inspection systems immediately examine every finished package. Vision cameras verify lid placement, foil integrity, printed graphics, and can shape, while check weighers confirm the correct product quantity. Containers showing dents, incomplete seals, incorrect weights, or visible defects leave the production line automatically through high-speed rejection systems. Accepted cans continue without interruption towards secondary packaging. Printed cans merge into carefully controlled groups before entering cartoning or shrink wrapping systems, depending on retail format. Some products receive paperboard trays with shrink film tightly wrapped around multiple cans, while others enter fully enclosed cartons formed automatically from flat blanks. Folding mechanisms close every panel before adhesive systems secure the finished package. Throughout this section, sensors continuously verify package count and orientation, ensuring every retail configuration leaves the line exactly as intended. Nerds candy begins making its unmistakable crunch long before the colorful shells appear, because the tiny crystal hidden at the center of every piece decides everything that happens afterward. At first, those future candies are almost impossible to notice as they travel through enclosed processing equipment. They are nothing more than microscopic sugar crystals moving steadily through the factory. Yet over the next several hours, those tiny particles will grow layer by layer into brightly colored nuggets with their familiar irregular shape. Every rotation inside enormous coating drums adds another microscopic layer, and every pause between coatings determines whether the finished candy develops the sharp crunch that makes nerds instantly recognizable. What looks like one simple candy is actually the result of hundreds of repeated transformations that slowly build outward from an almost invisible starting point. The process begins with the preparation of highly refined sugar solutions that will later become both the growing candy centers and the colorful outer shell. Granulated sugar enters enclosed stainless steel dissolving tanks through automated feeding systems, while carefully measured water flows in through temperature-controlled pipelines. powerful agitators begin circulating the mixture immediately, preventing crystals from collecting at the bottom while gradually producing a perfectly clear syrup. Heating jackets surrounding the tanks raise the temperature in a controlled manner until every grain disappears into solution. At this stage, the liquid looks almost transparent, despite containing enormous quantities of dissolved sugar. Sensors continuously monitor concentration, temperature, and flow, because even slight differences influence how the syrup behaves during later crystallization. The finished syrup travels through filtration equipment that removes any remaining particles before entering vacuum, cooking vessels. Inside these enclosed chambers, pressure drops dramatically, allowing water to evaporate at lower temperatures than would otherwise be possible. As moisture leaves the syrup, the dissolved sugar concentration rises steadily until the liquid becomes thick, glossy, and highly supersaturated. Pumps keep the dense syrup moving continuously while computerized controls monitor every stage of concentration. The objective is to prepare a syrup that is eager to crystallize but remain stable until the precise moment the factory decides to begin that transformation. Hidden inside this seemingly calm liquid is the energy that will soon build thousands upon thousands of candy pieces. Now, the factory reaches one of its most fascinating stages. Instead of pouring the concentrated syrup into molds, controlled crystallization begins around countless microscopic seed crystals. These tiny particles enter specialized coating equipment where the supersaturated syrup contacts their surfaces. The dissolved sugar immediately begins attaching itself to the existing crystals, forming an extremely thin solid layer. At first, the change is almost impossible to see. Each crystal grows only slightly larger, but this is only the beginning. Every future layer depends on this first microscopic coating remaining smooth and stable. The next stage repeats this operation again and again, gradually transforming nearly invisible particles into recognizable candy. Large rotating coating pans slowly tumble the growing candy centers, while precision spray systems introduce carefully measured quantities of concentrated syrup. Warm air flows continuously through the rotating pans, removing moisture from every newly applied coating before another layer arrives. The sequence repeats endlessly: spray, tumble, dry, rotate, spray again. Each cycle deposits another paper-thin layer of crystallized sugar. Thousands of tiny pieces move together inside every drum, constantly rolling over one another while maintaining surprisingly uniform growth. Hours pass, yet the candies continue increasing in size almost imperceptibly with every revolution. The slow pace is exactly what gives nerds their characteristic dense texture and sharp crunch. As the centers grow larger, additional process controls become increasingly important. Air temperature, humidity, drum rotation speed, syrup flow, and drying time must remain carefully synchronized. If syrup arrives too quickly, neighboring candies stick together. If drying proceeds too aggressively, surface defects begin forming before the next layer attaches. Automated control systems continuously adjust airflow and spraying intervals to maintain ideal conditions. Although each candy follows its own random path inside the rotating drum, every piece experiences nearly identical processing by the time the growth stage concludes. Once the desired size has been reached, the candy centers move toward another sequence that changes their appearance dramatically. Until now, they remain relatively plain in color. The brilliant shades associated with nerds have not yet appeared. Color preparation has been happening separately inside enclosed blending vessels where concentrated color solutions are dissolved into carefully prepared sugar syrups. Depending on the intended variety, different tanks prepare vibrant reds, blues, purples, oranges, pinks, yellows, or greens. Every solution is filtered before reaching the coating systems, ensuring perfectly smooth application during the next stage. The growing candies return to rotating coating pans, but now each syrup application carries color, as well as additional sugar. Thin colored layers build gradually across every surface, while heated air removes moisture between applications. Rather than applying one heavy coat, the process builds the final appearance through many extremely light coatings. Each pass deepens color intensity while preserving the irregular surface texture that gives nerds their distinctive appearance. As the candies tumble continuously, every edge and corner receives repeated exposure to the flowing syrup until vibrant color surrounds the entire piece. Color alone does not create the finished candy. Flavor development now begins through another carefully controlled coating sequence. Concentrated flavor systems prepared in separate blending vessels join the syrup stream, feeding the coating pans. Fruit flavors such as strawberry, grape, watermelon, cherry, orange, lemon, or tropical combinations disperse evenly throughout the thin syrup before contacting the candy. Each new coating contributes both sweetness and flavor, while gradually increasing the overall thickness of the outer shell. Although the candies still appear nearly finished, another important transformation waits ahead that gives nerds their unmistakable balance of sweetness and tanginess. Acid solutions are prepared independently using carefully measured food acids dissolved into controlled liquid systems. These solutions enter the coating process through precisely metered spray equipment. As the candies tumble inside the rotating drums, alternating layers of flavored syrup and acidic coatings gradually establish the familiar taste profile. Every rotation distributes the liquids evenly, while warm drying air locks each layer into place before the next application begins. The process continues until sweetness, acidity, color, and crunch reach their intended balance. Tiny adjustments to acid concentration or coating thickness can noticeably change the finished flavor, making this stage one of the most carefully monitored in the entire factory. Once coating is complete, the candies enter an extended conditioning stage. They move into controlled environments where temperature and humidity remain remarkably stable. During this period, residual moisture continues migrating throughout every candy while the outer shell hardens completely. The slow conditioning process strengthens the crisp texture without introducing cracks or unwanted surface defects. Although the candies appear finished, this resting period quietly determines how they will feel when bitten. Skipping it would leave the shell softer and less stable during packaging. The conditioned candies now travel across vibrating conveyors toward inspection equipment. Fine screens separate undersized fragments, while oversized pieces move towards separate handling systems. Optical sorting machines scan every candy at extraordinary speed, evaluating color, size, and overall appearance. High-speed air jets remove any piece that falls outside specification without interrupting the continuous product flow. Because the candies move individually across the inspection belts, every single piece receives attention before continuing deeper into production. Whipped cream production begins with liquid cream being standardized to the exact fat level needed for stable whipping. The cream arrives cold through stainless steel lines. It is not yet foam. It is a dense dairy liquid with fat droplets suspended in water, milk proteins, lactose, and minerals. Before it can become whipped cream, the fat level must be adjusted, the mixture must be blended with stabilizing ingredients, and the product must be treated, chilled, aerated, or packed for whipping later. In a dairy plant, raw milk is first separated into skim milk and cream. The milk enters a centrifugal separator, spinning at high speed. The heavier skim phase moves outward, while the lighter fat-rich cream collects closer to the center. The separator discharges both streams continuously. The cream stream is measured for fat content. If it is too rich, a controlled amount of skim milk can be blended back in. If it is too lean, more concentrated cream is added. This standardization creates a cream base with the correct fat percentage for the product being made. Whipping cream needs enough fat to trap air and form a stable foam. The fat droplets partially connect during whipping, building a network around air bubbles. If the fat is too low, the foam collapses quickly. If the fat is too high, the cream can become overly thick or churn toward butter. The standardized cream enters a blending tank. The tank is jacketed for temperature control and fitted with a slow agitator. Sugar may be added for sweetened whipped cream. Stabilizers or emulsifiers may be added in small measured quantities to help the foam hold shape. The dry ingredients are not dumped into still cream. They are drawn into a moving liquid stream. A powder induction system can pull sugar or stabilizers into the cream and disperse them rapidly. This prevents clumps from forming on the surface. The cream remains cold during blending. The agitator turns slowly enough to avoid accidental whipping. At this stage, the goal is uniform liquid, not foam. Every ingredient must dissolve or disperse without trapping large air pockets. The blended cream passes through filtration. Fine screens remove undissolved particles and protect downstream valves, nozzles, and filling equipment. The liquid then moves toward heat treatment. Pasteurization is performed in a closed heat exchanger. The cream travels through narrow stainless steel channels, while hot water or steam-heated fluid flows on the opposite side of thin plates. Heat transfers quickly into the cream. The mixture reaches the required treatment temperature while remaining enclosed in the system. The heated cream may pass through a holding tube for a controlled time. This ensures the entire stream receives the intended heat treatment. The flow rate and tube length determine the holding time. After heating, the cream immediately enters a cooling section. Chilled fluid pulls heat away through the stainless steel plates. The cream temperature drops rapidly, preserving the dairy structure and preparing it for aging. Homogenization may be controlled differently depending on the whipped cream type. Some cream products are lightly homogenized or not homogenized in the same way as milk because large enough fat droplets help whipping. If homogenization is used, pressure settings are chosen carefully so the cream remains capable of forming stable foam. The cooled cream enters aging tanks. These tanks hold the cream cold while the fat crystallizes into the right structure for whipping. Slow agitation keeps the ingredients evenly distributed without introducing too much air. The cream becomes slightly thicker as it rests. Aging is important because cold fat behaves differently from warm fat. Properly crystallized fat droplets can partially join during whipping and support the foam. Without enough cold aging, the cream may whip poorly or lose volume quickly. From this point, production can follow two main factory routes. One route produces ready whipped cream in tubs. The other produces aerosol whipped cream in pressurized cans. Both begin with the same controlled liquid cream base, but they handle air and packaging differently. For ready whipped cream, the aged cream is pumped into a continuous whipping machine. The machine introduces filtered air, or gas, while mechanical beaters shear the cream. Rotating elements break the gas into tiny bubbles and spread them through the liquid. The cream changes rapidly. It becomes lighter in color, thicker, and more voluminous. The fat droplets partially connect around the bubbles, forming a foam network. The mixture no longer flows like liquid cream. It moves as a soft, structured foam. The whipping machine controls overrun, which is the amount of air incorporated into the cream. Too little air produces a heavy product. Too much air creates weak foam that collapses. The machine balances feed rate, beater speed, temperature, and gas flow. The whipped cream exits through a short pipe toward the filler. Long pipe runs are avoided because excessive pumping can damage the foam. The product is soft and delicate, so every transfer must preserve its structure. Empty tubs or cups feed into the filling line. They are separated from nested stacks and placed into pockets on a conveyor. Each container arrives beneath a filling nozzle. The nozzle deposits whipped cream into the container with controlled movement. The product enters as a thick spiral or mound. The foam must fill the container without large voids, but it must not be crushed by high pressure. After filling, a lidding machine places a lid onto each tub. The lid is pressed into place or heat sealed depending on the package. The container now protects the whipped foam from mechanical damage and air exposure. The filled tubs move through check weighing and inspection. A check weigher verifies that each tub contains the correct amount. Cameras check lid position, container shape, and seal condition. Rejected tubs are removed automatically. For aerosol whipped cream, the process is different after aging. The cold liquid cream base is filled into metal cans instead of being whipped before packaging. Empty aerosol cans arrive open at the top and move through cleaning and positioning equipment. The cans are held upright in pockets or star wheels. A liquid filler doses a precise amount of cream into each can. The cream remains mostly liquid at this stage. It has the correct fat, sweetness, stabilizer system, and temperature, but it will foam only when dispensed later through the valve. After the cream dose enters, the can receives a valve assembly. The valve is positioned over the opening. A crimping head presses the valve cup onto the can and mechanically seals it around the rim. This creates a pressure-tight closure. A propellant gas, commonly nitrous oxide for whipped cream systems, is then added through the valve or during the filling sequence. The gas dissolves partly into the cream under pressure. The can is designed to hold this pressure safely and release the product as foam when the valve is opened. The sealed can may pass through shaking or mixing equipment, so the gas and cream distribute evenly. The can remains cold to maintain product quality and pressure behavior. Each aerosol can then moves through leak testing. Equipment checks whether the crimp and valve are sealed correctly. A leaking can is rejected. Weight checks confirm that the proper amount of cream and gas is present. The can receives a plastic actuator and cap. The actuator fits over the valve stem and controls dispensing. The cap protects the actuator during handling. Machines place these components at high speed while cans continue moving along the conveyor. Labels may be applied if the cans are not already printed. In a labeled can line, pressure-sensitive labels peel from a backing web and wrap around the cylindrical can. Rollers press them flat. Printed cans bypass this stage and move directly to coding. Coding equipment marks each package with production information. Inkjet printers apply small characters to the tub, lid, can base, or label. The mark is checked by vision systems as the package passes. Hard candy only has two useful states on a lollipop line: fluid enough to be shaped and glassy enough to hold its shape. Chupa Chups style production is built to push the candy through that transition at the exact moment a stick is inserted and locked, then isolate the finished piece from humidity so it never leaves the glassy state. The most reliable way to understand the factory is to start at the forming wheel, because every upstream system exists to feed that wheel at a stable rhythm. The forming wheel is an indexed machine with cavities that open, receive a dose of hot candy, accept a stick, close to shape, then release the lollipop. Its speed is fixed by output targets, so the candy mass must arrive at the depositor at the correct temperature and viscosity, and sticks must arrive at the inserter in the correct orientation and at the correct moment. Stick handling runs continuously. Sticks are cut to length if not pre-cut, then screened to remove splinters. A deburring or air cleaning stage strips dust because dust at the interface weakens bonding and creates voids. Sticks are then singulated into individual lanes. Singulation is a mechanical sorting problem. Sticks are light and can overlap, so feeders rely on vibration, step conveyors, and guide rails to separate them. Orientation is enforced, so the same end enters the candy each time. The stick feed ends at a pick-and-place head or pusher that inserts the stick into the cavity at a fixed depth. Depth stops are mechanical, so insertion depth remains consistent even if stick length varies slightly. Depth matters because too shallow reduces pull strength, and too deep can create internal stress rings that lead to cracking. While sticks are being fed, the candy mass is being prepared as a concentrated syrup that will set into a clear glass. Sugar is stored dry and screened, so clumps do not enter dissolving. Water is filtered and tempered because inlet temperature affects dissolution speed and cook stability. Glucose syrup is held in jacketed tanks, so viscosity stays stable for pumping, and it functions as a crystallization control ingredient. These streams combine in a dissolver, where heat and agitation create a clear solution. The target is full dissolution with no visible grains, because undissolved grains become nucleation sites that can trigger graining later, making the candy cloudy and brittle in an unpredictable way. Concentration is performed rapidly to reach hard candy solids. In a continuous system, the clear syrup is pumped through heated coils under pressure, allowing temperature to rise quickly without boiling inside the tube. A flash chamber then reduces pressure so a portion of water instantly vaporizes and exits as steam. This flash step tightens final moisture and also reduces thermal damage because water removal occurs at a lower effective temperature than extended open boiling. Final moisture content is the main structural setting. Too much moisture yields candy that stays tacky and softens quickly. Too little moisture yields candy that becomes overly brittle and cracks at the stick interface during cooling or later handling. Immediately after concentration, the mass enters a controlled cooling section. The aim is to bring the mass to a forming temperature that is still fluid enough to be deposited and shaped, but not so hot that it degrades flavor, and not so cool that it begins to set in pipes. Heat exchangers and jacketed manifolds manage this temperature precisely. At this stage, additives are introduced because many flavors contain volatile compounds that would be stripped or damaged at peak cooking temperatures. Color is prepared as concentrated solutions or dispersions and filtered so no particles clog injectors or create specks. Flavor is metered by precision pumps into the candy stream. Injection is placed after the main heat load so aromatics are preserved. Acid can be introduced as a solution if the recipe calls for a sharper profile, but acid timing is controlled because acid accelerates sucrose inversion at high temperature, which changes viscosity and long-term stickiness. Mixing after injection is done with static mixers or low-shear mixing manifolds that fold the flow and eliminate streaks without entraining air. Air entrapment is undesirable because bubbles create weak zones and can appear as surface pits once the candy cools. The candy mass then feeds the depositor at the forming wheel. The depositor meters a precise amount into each cavity. Portion volume directly sets lollipop size and weight. Metering is done by piston pumps or gear pumps synchronized to the wheel index. Dose accuracy matters because a low fill yields thin spots and poor stick anchoring, while an overfill creates flash that must be trimmed and increases wrapper puncture risk. The cavity receives the candy dose first or simultaneously with stick insertion depending on machine design. In one approach, the cavity is partially filled, then the stick is inserted, then a second small dose tops off and the cavity closes. In another approach, the cavity closes on a measured candy slug and the stick is driven into it. The common requirement is that candy must be plastic at the moment the stick enters, so the candy wets the stick surface and bonds as it cools. Shaping occurs when the cavity closes. The closing motion forces candy into the spherical geometry and expels trapped air. Venting channels can allow small air pockets to escape so they do not remain as bubbles. Cavity surface finish is polished, so the candy skin releases cleanly. Cavity temperature is managed so candy does not stick or smear. If cavities are too cold, the candy skin sets instantly and can trap air. If cavities are too warm, the candy remains tacky and can deform during demolding. The machine therefore maintains a stable mold temperature through internal circulation. As the formed lollipop exits the cavity, it is still hot enough that the interior is not fully glassy. It immediately enters a cooling system that locks structure. Cooling is staged. The first stage sets the outer surface quickly so the shape stops flowing. This can be done with cool, dry air directed at the candy surfaces. The second stage brings the core temperature down so the entire mass crosses into the glass state. Cooling rate must be controlled because excessive thermal gradients create stress. Stress tends to concentrate around the stick insertion zone because the stick acts as a rigid inclusion and the candy contracts around it. If the outer layer contracts much faster than the inner, microcracks can form. These cracks may be invisible initially, but can propagate during shipping or when humidity changes. Humidity control in cooling is essential. Hard candy absorbs moisture from air. If cooling air is humid, a thin moisture film can form on the warm candy surface. This film dissolves sugar at the surface and then recrystallizes as a rough haze, reducing gloss and increasing stickiness. Cooling tunnels therefore use dry air. Some lines control dew point directly, keeping dew point low enough that condensation cannot form on the candy at any point in the tunnel. Once cooled to handling temperature, lollipops are demolded or released from the forming wheel and transferred to conveyors. Transfer points are designed to avoid impact at the candy head because the surface can still mark if it is too warm. Guides support sticks rather than candy heads because contacting the head can create flat spots. The lollipops pass through inspection and rejection systems. Vision systems can detect off-center sticks, incomplete fill, surface bubbles, and flash around seams. Weight checks can detect underfill and overfill. Reject mechanisms remove defective pieces before wrapping because wrapping a defective piece wastes film and creates downstream jams. Twizzlers are manufactured by converting a cooked sweet base into a plastic, elastic candy dough, shaping that dough continuously through extrusion, setting texture through staged drying and cooling, then cutting and wrapping so the ropes stay chewy and separate without sticking. The most useful place to start is the cutter, because the cutter reveals whether the upstream dough has the right cohesion and whether the rope has been set enough to hold its geometry. If the rope tears at the cut, the dough is underhydrated or too cold. If it smears and strings, the dough is too warm or too wet. The factory therefore tunes the entire process to deliver an extrudate that behaves predictably at the knife. Upstream of the cutter, the rope travels through setting tunnels that control moisture and temperature. Those tunnels are what convert an extruded ribbon into a stable Twizzlers rope with a uniform chew. The rope exits the die warm and pliable, and its interior still contains enough water to make it sticky if packaged immediately. The setting tunnel removes a measured amount of moisture while allowing the matrix to equilibrate so the surface becomes dry enough to handle, yet the core remains chewy. Air temperature, humidity, and velocity are balanced to avoid case hardening. Case hardening creates a tough outer shell and a soft interior, which leads to cracking during bending and an uneven bite. Staged zones, warmer early zones, and gentler later zones reduce that risk. Before the rope ever reaches those tunnels, the line creates the candy dough in a cooker and mixer system designed for high solids. Sugar and glucose syrup are staged as the main carbohydrate system. Granulated sugar is screened to remove clumps and dust because clumps dissolve unevenly and dust can scorch at hot surfaces. Glucose syrup is held in jacketed tanks so viscosity stays stable for metering. Water is filtered and tempered because inlet temperature shifts dissolution and cook stability. Starch and other structure-building solids are held dry and fed accurately because their hydration rate determines dough firmness later. Cooking starts in a dissolver where sugar is hydrated into a clear solution. That solution then moves to a cooker where heat drives off water and raises solids. The cook endpoint is selected so the base becomes plastic when cooled, not glassy like hard candy, and not fluid like syrup. The endpoint is typically controlled by temperature and by flow resistance in the cooker. If the base is undercooked, it carries too much water and produces a sticky rope that never sets. If overcooked, it becomes too stiff, causing high extruder pressure and surface cracking at the die. After cooking, the hot base is cooled into a window where powders can be incorporated without clumping, and flavors can be added without being stripped. At this stage, the line transitions from a boiling syrup process to a dough making process. Structure formers, like starches, must be dispersed and hydrated evenly. Dry starch added directly to hot syrup would form lumps with dry cores. To avoid that, starch can be fed through high shear mixers or introduced as a slurry that is hydrated and cooked separately before blending. The goal is a continuous matrix where starch and sugars form a cohesive network. Acids and salt are staged as low-rate additions. Acid influences flavor and also changes the behavior of the carbohydrate matrix over time by shifting inversion and hygroscopicity. For that reason, acids are added after the hottest zones and mixed thoroughly but gently. Flavor and color are also added late. Flavor injection is done downstream of intense heat to preserve volatile components. Color is metered as a concentrated solution to avoid adding excess water. Once all components are combined, the mass enters intensive mixing. This is where it becomes a uniform plastic dough. The mixer uses high torque elements that fold and shear. Shear must be sufficient to eliminate streaks and fully wet powders. Shear must not be so aggressive that it whips air into the dough, because trapped air causes bubbles and weak spots in the extruded rope. Mixing endpoint is judged by uniform color, uniform torque, and a stable temperature. Temperature is monitored continuously because the dough must remain plastic but not overly soft. The dough then enters a conditioning stage before extrusion. Conditioning equalizes moisture throughout the mass and stabilizes temperature so extrusion pressure does not pulse. This can be done in a holding hopper with gentle agitation or in a screw conveyor that provides a fixed residence time. The objective is to deliver the extruder a steady feed that produces a steady rope diameter. Extrusion is the primary shaping method. The dough is fed into a screw extruder whose barrel is temperature controlled. The screw compresses and pushes the dough forward. Compression removes minor voids and increases cohesion. Barrel temperature keeps the dough in the plastic range. If the barrel is too cool, pressure rises and the rope surface becomes rough. If too warm, the rope surface becomes tacky and can collapse after exiting the die. The die defines rope, cross-section. Twizzlers ropes are typically round or slightly shaped, depending on the product format. Die temperature is controlled because cold dies cause surface tearing and hot dies cause smear. Pressure at the die is monitored. It acts as an indicator of dough viscosity and hydration. Stable pressure produces stable diameter, which matters because diameter controls final chew and package weight. Immediately after extrusion, the rope is guided by takeoff belts. Belt speed must match extruder output to avoid stretching. Stretching thins the rope and aligns the matrix, which can make the bite tougher and can produce uneven twist definition. The rope is supported so it does not sag, because sag introduces diameter variation and can cause twists to tighten unevenly. Twist formation, when used, is produced by controlled rotation relative to forward motion. A twisting head grips the rope or imparts rotation while the takeoff belt pulls. The twist pitch is set by the ratio of rotational speed to linear speed. A tighter pitch yields a more pronounced twist and slightly denser bite. A looser pitch yields a smoother rope and a softer feel. Twist must be consistent along the rope, because variation creates weak points where the rope can split during cutting or packaging. After twisting, the rope enters the staged drying and cooling tunnels described at the beginning. These tunnels are engineered to hit a final moisture endpoint that supports chew without stickiness. Early tunnel zones focus on removing surface moisture so the rope can be handled without clumping. Later zones allow moisture to migrate from the core to the surface gradually and leave the rope at a stable water activity. Airflow is controlled to avoid whipping ropes into each other, and the rope is kept separated by lane guides. Once the rope reaches the target set, it passes to cutting. Cutting uses rotary blades, or guillotine cutters, synchronized to belt speed. Synchronization controls piece length and therefore piece weight. Blade sharpness is managed because a dull blade drags and creates strings at the ends. Stringing is a sign that the rope is still too warm or too wet. A clean cut indicates the surface has set and the interior has enough cohesion to fracture neatly at the blade. Cut pieces then go through a short post-set stage. This allows freshly cut ends to dry slightly so pieces do not stick end to end. It also allows any residual heat from cutting friction to dissipate. If a light surface treatment is used to improve flow, it is applied here. A tiny amount of neutral oil can be misted while pieces tumble gently. The oil film reduces surface friction and helps prevent sticking in the wrapper. Oil application is minimal because excess oil changes mouthfeel and attracts dust. Screening can follow to remove fragments created during cutting and conveying. Removing fragments improves pack appearance and reduces dust that can interfere with seals. Metal detection or other final integrity checks can be positioned here because product flow is stable and pieces are separated. Wrapping begins with controlled feeding into flow wrappers. Pieces are aligned into lanes and spaced, so each wrapper cycle receives one piece. Film is formed around the rope and sealed with heat and pressure. Seal dwell and temperature are tuned, so seals are strong without overheating the candy surface, because overheating can soften the rope and deform it under film tension. Film tension is controlled so it sits snug without squeezing the rope flat. Slush. Puppy-style slush is manufactured by producing a shelf-stable flavored concentrate, then engineering a dispensing system that freezes a diluted beverage into a suspension of tiny ice crystals without forming a solid block, then keeping those crystals moving so the product stays scoopable and uniform in a cup. The easiest way to understand the production chain is to start at the point of consumption, the slush machine. A slush machine is essentially a controlled, scraped surface freezer that must keep a mixture right at its freezing curve. It needs enough sugar and solutes to depress the freezing point, enough viscosity to keep ice crystals suspended, and enough agitation to prevent large crystals from growing. Everything that happens in the factory is designed to make a concentrate that, when diluted, behaves correctly inside that machine. The slush machine relies on a mix ratio that is tightly defined. The concentrate is not used full strength. It is diluted with water to a target sugar concentration. If the mix is too weak, freezing point rises and the machine produces a hard ice mass or large crystals that separate into watery and icy zones. If the mix is too strong, freezing point drops too far and the machine struggles to freeze enough, yielding a cold syrup rather than slush. That is why the factory builds the concentrate with a known soluble solids level and a known acidity, and why it specifies a dilution ratio. Concentrate manufacturing begins with water handling and sweetener preparation. Water is filtered to remove suspended solids because solids can seed haze and clog dosing valves. The main sweetener can be sugar syrup, glucose syrup, or a blend. For sugar-based concentrates, granulated sugar is dissolved in heated tanks with agitation until the solution becomes clear. Density is monitored because it defines sweetness and freezing behavior after dilution. For syrup-based sweeteners, the syrup is held warm, so viscosity is stable, and metering is accurate. Acidity is set next because pH affects flavor perception and stability. Acid is prepared as a liquid solution for accurate dosing and then injected into the blending tank. pH is measured and adjusted to a narrow set point. A stable pH also helps preserve certain flavor components. Color is handled as a separate dosing stream. It is stored in tanks with gentle mixing and filtered before dosing so it remains uniform. Flavor is prepared as a concentrate that can be dispersed reliably in water. Many slush flavors contain both water-soluble aroma components and oil-based notes. Oil-based components are emulsified, so they do not separate in the finished concentrate. Emulsification is done with high shear mixers that reduce droplet size. Droplet size matters because large droplets separate and ring at the surface, while small droplets remain stable and deliver consistent aroma. The finished flavor concentrate is filtered to remove particulate and then metered into the main blending tank. Viscosity modifiers can be included in small amounts to influence mouthfeel and crystal suspension. These components must be fully hydrated and dispersed, so they are added under controlled shear and allowed to mix until uniform. The goal is not a thick beverage, but a mix that can hold microcrystals evenly during dispensing and drinking. Once sweetener, acid, color, flavor, and any stabilizers are in the blending tank, the concentrate is mixed to uniformity without entraining air. Air entrainment can cause foaming in packaging and can affect how the concentrate mixes with water later. The concentrate is then filtered to remove any remaining undissolved particles that could settle or clog dispensing systems at retail. Quality checks on the concentrate focus on soluble solids, pH, color density, and flavor strength. Soluble solids are measured to ensure the dilution ratio will yield the intended freezing point depression. pH is checked for consistency because it affects taste and stability. Color is checked because it must remain stable in storage and consistent from batch to batch. The concentrate then moves to packaging. Packaging is designed for high sugar liquids. Concentrate is filled into jugs, bottles, or bag-in-box systems. Bag-in-box is common because it minimizes oxygen exposure and allows easy dispensing at retail. Filling uses metered valves and is controlled to avoid splashing and foaming. Caps or fitments are applied immediately. Seals are checked because leaks allow contamination and sugar crystallization around closures. Finished packages are coated and cased. At retail, the concentrate is mixed with water to the specified ratio. That mixing can be done in a separate tank or directly in the machine reservoir. The purpose is to produce a ready mix with the correct sugar concentration and acidity. The water used at retail can vary. So many systems specify filtration and cold water use to reduce variability. Inside the slush machine, freezing is achieved by a refrigerated cylinder and a rotating scraper. The cylinder wall is cooled below the freezing point of the mix. A thin layer of ice forms on the cold wall. The scraper continuously removes that ice layer and breaks it into small crystals that are pushed into the bulk liquid. Continuous scraping prevents the ice from building into a solid sheet that would block heat transfer. The rotating mechanism also keeps the entire mixture moving so ice crystals remain suspended rather than settling. The formation of microcrystals is controlled by the freezing point depression of the mix. Sugar and dissolved solids lower the freezing point so the mixture does not freeze solid at typical machine temperatures. Instead, a fraction of the water freezes as ice, while the remaining liquid becomes more concentrated. This concentrated liquid phase acts as a lubricating syrup between ice crystals. The machine aims for a steady balance where ice fraction stays in a target range. Agitation speed is a key control. If agitation is too slow, ice crystals grow larger and the product becomes coarse and icy. If agitation is too fast, the mixture can incorporate air and become foamy, and frictional heat can reduce freezing efficiency. The scraper geometry and clearance are engineered to remove ice efficiently without creating excessive shear that would heat the mixture. The machine also relies on viscosity to prevent separation. If the liquid phase is too thin, ice crystals can settle and form a dense, icy bottom layer, while the top becomes watery. A slightly more viscous liquid phase helps keep crystals evenly distributed. This is why concentrates often include small amounts of stabilizer and why the soluble solids level is strictly maintained. Temperature control in the machine is staged through a thermostat system that cycles refrigeration. The goal is not a constant deep freeze, but a controlled temperature near the mixer's freezing curve. If the machine overcools, ice fraction rises too high, and the product becomes stiff and difficult to dispense. If it undercools, ice fraction drops, and the product becomes slushy syrup. Machines often use sensors that monitor torque on the agitator as an indirect measure of slush stiffness, adjusting cooling accordingly. From a factory perspective, this machine behavior drives the formulation targets. The concentrate must produce a ready mix with a predictable freezing curve. That means controlling sugar type and concentration. Different sugars and syrups depress freezing point differently and change viscosity. The factory chooses a sweetener system that creates the desired crystal fraction at typical machine temperatures. Acidity and flavor intensity are also tuned with the machine in mind. Cold temperatures reduce flavor perception. Therefore, the ready mix is formulated with enough flavor concentration to remain noticeable when frozen. Acidity can provide brightness that cuts through cold dullness. However, acidity also affects the stability of certain emulsions and can influence syrup behavior over time. The factory balances these factors. Color stability is another practical requirement. Slush is displayed in clear machine bowls and must remain visually uniform. Colorants must remain stable under light exposure and cold temperatures. The factory filters concentrate to remove particles that would settle and create gradient bands. Barilla-style pasta takes its first shape when coarse golden semolina and water are pressed into a dense dough under vacuum. The semolina does not enter like fine cake flour. It is granular, sandy, and yellow from durum wheat. It flows from storage silos through enclosed pipes and weighing systems. Screens remove oversized particles. Magnets catch stray metal fragments. The semolina drops into the mixer as a dry, rough stream that will become pasta only after hydration, pressure, shaping, and slow drying. Water enters through a metered line. The amount is small compared with bread dough. Pasta dough is intentionally stiff. It is not soft, elastic, or fluffy. It is a compact mixture built to be forced through metal dies. As water hits the semolina, the grains darken and swell. The first change is quiet but important. Dry particles begin binding into damp crumbs. The mixer turns with heavy paddles. It does not whip air into the dough. It folds the semolina and water together until the mixture becomes evenly hydrated. At this stage, the dough looks more like wet sand than a smooth mass. That rough texture is exactly what the extruder needs. The real transformation is still coming. Before extrusion, the dough passes through vacuum. Air is pulled out of the mixing chamber. Tiny bubbles trapped between semolina particles disappear. This matters because air pockets would create weak spots, pale streaks, and rough breaks in the finished pasta. Under vacuum, the dough becomes denser and more uniform. Now, the pressure begins. A large screw inside the extruder pushes the stiff dough forward. The screw rotates inside a barrel, compressing the mixture with every turn. The dough becomes warmer from friction and pressure, but temperature is controlled so the starch and protein do not cook. The mass moves slowly toward the die head like thick clay being forced through a narrow opening. The die decides the pasta shape. Every tube, strand, shell, twist, ribbon, and hollow form comes from the geometry of the die. The dough has no final identity until it reaches this metal plate. What enters the die as compact semolina dough exits as spaghetti, penne, macaroni, fusilli, rigatoni, or another shape. For spaghetti, the die contains many small round holes. The dough pushes through them and exits as long continuous strands. These strands drop downward in parallel lines, still flexible and damp. They shine slightly at the surface because the dough has just been compressed through metal. For penne, the die forms tubes. The dough flows around small internal pins that create the hollow center. As the tubes emerge, rotating blades cut them at an angle. Each cut creates the slanted ends that make penne recognizable. The pieces fall away in short lengths, still soft enough to bend, but firm enough to hold their hollow shape. For macaroni, curved tubes are shaped by dies that force the dough through bent channels or guide it into a curved path as it exits. For rigatoni, the die forms wide tubes, and ridges may be created by the die surface or shaping elements. For fusilli, the dough twists as it exits or is shaped by rotating guides that create a spiral. This is the hook inside pasta production. The same dough can become dozens of different products simply by changing the metal path it is forced through. The surface texture also depends on the die. Smooth dies create pasta with a cleaner, more polished surface. Bronze dies create a rougher texture because the dough drags against the metal more heavily. That rough surface catches sauce better, but it also requires careful drying because the texture holds moisture differently. Freshly extruded pasta contains too much moisture to be packed as dry pasta. It must be dried without cracking, bending, sticking, or collapsing. This drying stage is slower and more delicate than the extrusion itself. Long pasta follows one route. Spaghetti strands are lifted onto rods or spread across support systems so they hang straight. The strands must not touch too heavily, or they can stick together before their surfaces dry. The line keeps them separated while they enter the first drying zone. Short pasta follows another route. Penne, fusilli, shells, elbows, and rigatoni fall onto vibrating conveyors or perforated belts. The movement spreads the pieces into a shallow layer. Air can move around them from above and below. Pieces that clump together are separated before drying becomes permanent. The first drying stage is called pre-drying. Warm air removes surface moisture quickly. The outside of the pasta firms, just enough to prevent sticking, but the inside is still moist. If the surface dried too hard, too fast, moisture trapped inside would create cracks later. The process has to dry the outside without sealing the inside. The pasta then enters longer drying chambers. Temperature and humidity are controlled in stages. Warm air flows across the product, carrying moisture away. The pasta slowly loses water from the center outward. The goal is to bring moisture down to a stable level while preserving shape, color, and strength. Inside the pasta, starch granules and gluten. Proteins form a rigid network as water leaves. The structure becomes hard and glassy. A soft, damp tube becomes a dry piece that can survive packing, shipping, and later boiling. The transformation is not just moisture loss. It is the creation of a stable internal architecture. Drying too quickly creates stress. The outside contracts before the center can shrink, and the pasta may crack. Drying too slowly wastes time and can weaken texture. The drying tunnel uses different zones so the pasta can adjust gradually. Heat, humidity, airflow, and residence time all work together. Long pasta must stay straight during drying. Hanging strands pass through zones where air moves evenly around them. If one side dries faster than the other, the strand can curve. The line controls airflow so each strand remains aligned. Short pasta must keep its shape. Hollow tubes cannot collapse. Spirals cannot unwind. Shells cannot flatten. The early drying step locks the shape, and the later drying steps strengthen it. Vibrating belts and perforated trays prevent pieces from piling too deeply. After drying, pasta enters a cooling zone. The hot, dry pasta cannot go directly into packaging. If packed while warm, trapped heat could create condensation inside the package. Cooling air brings the pasta closer to room temperature while keeping it dry. Now the line listens for defects. The cooled pasta moves through screens and sorting equipment. Broken pieces, fines, and dust fall away. For short pasta, vibrating screens separate undersized fragments. For long pasta, cutting systems trim strands to the correct length, and broken strands are removed before packing. Optical sorters can inspect color and shape. Pale spots, dark specks, burnt fragments, cracks, or misshapen pieces are detected as the pasta passes under cameras. Air jets remove defective pieces from the flow. The accepted pasta continues forward as a clean, uniform stream. For spaghetti and other long pasta, the strands are gathered into measured portions. The product aligns lengthwise. Mechanical guides square the ends and form bundles. The strands must be straight enough to slide into cartons or bags without snapping. For short pasta, the pieces enter weighing hoppers. The pasta flows like dry ceramic shapes, rattling across stainless steel surfaces. A multi-head or linear weigher measures each portion. The machine releases the correct weight into the packaging system below. Packaging depends on the format. For bagged short pasta, printed film unwinds from a roll. The film passes over a forming collar and wraps into a tube. A vertical seal closes the back. Horizontal jaws create the bottom seal. The weighed pasta drops into the open package. The jaws close again above it, sealing the top and cutting the bag free. The bag must protect the pasta from moisture. Dry pasta is stable only because its moisture level is low. The package keeps outside humidity from softening the product before it is cooked. For boxed pasta, flat paperboard blanks feed into a cartoner. Suction cups open the blank into a rectangular carton. Pasta is weighed or measured and dropped into the open box. Flaps fold in sequence. Glue or locking tabs secure the closure. The carton exits squared, filled, and ready for coating. Long pasta often enters cartons through a horizontal loading system. Bundles of spaghetti slide into opened boxes. The bundle must enter cleanly without bending. Folding rails close the flaps around the pasta. Adhesive secures the box, while compression belts keep the shape square. Some pasta is packed in clear window boxes. The board carton includes a transparent film window. The pasta must align behind the window without dust or broken pieces clouding the view. The cartoner closes the box while keeping the window flat and clean. Every package passes through check weighing. Underfilled packs are rejected. Overfilled packs are also removed because they can strain seals or deform cartons. Vision systems check closure, print alignment, label position, and package shape. Metal detectors scan the sealed pack. Coding equipment prints production information onto the bag, box, or case. Inkjet or laser marks appear while the package moves at line speed. Scanners confirm that the code is present and readable. How do factories churn out Krispy Kreme donuts, Snickers, and Lay's at full speed without the texture falling apart? One wrong proof or one overfried chip can turn perfect into trash in seconds. In this documentary, we go behind the scenes from dough to fryers, uncovering the secret methods these brands use to make their products that they don't want you to know. The defining feature of a Krispy Kreme style ring donut is the thin, tender crust, and airy interior that come from a dough that is proofed to a narrow endpoint, fried with a controlled flip, then glazed while the surface is still warm enough to accept a uniform film without soaking. Everything is organized around the proof to fry handoff, so the line is built to keep dough pieces moving continuously from cutting to proofing to oil without waiting. The dough system starts with flour and liquid staged to produce a consistent final dough temperature. Flour is sieved to remove lumps and to stabilize flow into the mixer. Sugar is screened so crystal size does not vary significantly because sugar affects both fermentation rate and browning. Salt is weighed precisely to control dough strength and yeast activity. Yeast is prepared as a dry addition or slurry, so it disperses evenly. Fat is tempered so it blends smoothly without streaking. Water and dairy liquids are tempered because final dough temperature is one of the strongest predictors of proof time. Mixing builds a gluten network that can expand without tearing. The mixer begins at low speed to hydrate flour and incorporate yeast and sugar uniformly, then increases speed to develop gluten to a target elasticity. The target is not maximum strength. The dough must be strong enough to hold gas during proofing and frying, but extensible enough to sheet cleanly and cut without shrink. Fat is introduced after initial gluten development, so it softens the network rather than blocking formation. The mix endpoint is judged by dough smoothness and elasticity and by temperature. If the dough exits too warm, it will ferment too fast and become sticky on rollers. If too cool, it will be tight and resist expansion. After mixing, the dough enters a short rest to equalize moisture and relax gluten. Relaxation reduces snapback in sheeting, which is essential for ring accuracy. During this rest, early fermentation begins creating small gas cells. The rest is timed so the dough remains workable and does not overexpand before forming. Forming begins with sheeting. The dough passes through a series of reduction rollers that gradually decrease thickness. Large reductions are avoided because they create stress lines that show up as weak spots during frying. Gauge rollers at the end set the final sheet thickness, and that thickness becomes a primary determinant of donut weight and final crumb thickness. The sheet then enters rotary cutting, where an outer ring and an inner hole are cut in one motion. Cutter sharpness is critical because dull cutters compress the edges and create ragged rims that absorb more oil and brown unevenly. Scrap dough around the cutouts is lifted and recycled at controlled ratios because heavy recycling increases work input and changes dough strength. Cut rings are transferred onto proofing screens or belts with minimal distortion. Transfer height is kept low, and the dough is supported so it does not stretch. Stretching changes ring thickness and causes uneven expansion. The rings then enter the proofer, which is essentially a controlled fermentation chamber that raises the dough to near final volume. Proofing conditions are set to achieve rapid, even expansion without forming a surface skin. Temperature controls yeast activity. Humidity prevents the surface from drying and sealing, which would trap expanding gas and cause blisters. Proof time is tuned so the ring becomes light and inflated, yet still strong enough to be moved and flipped in oil. Underproof produces dense donuts with thicker crust and less lift. Overproof produces fragile rings that collapse when they hit the fryer or when they are turned. The fryer is designed to set the structure quickly while preserving a thin crust. Oil temperature is held in a narrow band and monitored continuously. When proofed rings enter the oil, surface water flashes to steam, creating outward pressure that expands the ring further and helps delay oil penetration in the earliest seconds. Starch gelatinizes at the surface and forms the initial crust. Proteins coagulate and lock structure. As the surface dries, browning begins and color develops. Rings typically fry one side first while floating. Conveyor speed sets the dwell on the first side, then a turning mechanism flips the ring. Flip timing is a major control because the first side must be set enough to support the ring during rotation, but not so overcooked that it becomes thick and dark. After the flip, the second side fry completes structure set and balances moisture loss. The total fry time is tuned to yield a pale, thin crust that remains tender rather than thick and crunchy. Oil management is continuous because crumbs and fragments break off and burn, darkening oil and changing heat transfer. Filtration removes fines. Oil circulation maintains uniform temperature across the fryer width. Fresh oil addition and controlled bleed maintain quality, so color remains consistent from hour to hour. Stable oil behavior is essential because even small changes in heat transfer shift crust thickness and glaze pickup. As rings leave the fryer, surface oil drains immediately. Drain belts and brief vibration shake off free oil. Removing surface oil matters because it affects glaze adhesion and prevents greasy patches that repel glaze. The donuts then move onto a short cooling conveyor, but the cooling is not intended to fully cool them. It is intended to bring the surface into the glaze window. Glaze is applied while the donut is still warm. The glaze is a sugar solution or suspension mixed to a defined solids level. Solids level determines film thickness and set speed. The glaze is held warm enough to flow smoothly, but not so hot that it becomes too thin. Donuts enter a glaze waterfall or curtain where glaze coats the surface. Excess glaze drains as donuts travel on a belt. The warm donut surface helps the glaze spread evenly and then set. If donuts are too hot, glaze becomes excessively thin and runs off, leaving a patchy coat. If too cool, glaze sets too quickly and creates uneven coverage and a grainy texture. After glazing, the donuts move through a setting zone where glaze crystallizes. Airflow here is controlled because strong airflow can dry glaze too fast and create a rough finish, while weak airflow can leave glaze tacky and prone to sticking in cartons. The objective is a smooth, thin glaze shell that remains slightly delicate and glossy. For filled products, filling is typically done after the donut has cooled further and the crust has stabilized. A controlled injection system uses needles to place a measured dose of filling. Filling viscosity is tuned so it flows through needles without tearing the crumb and then holds shape without leaking. Needle depth and dose volume are controlled so filling is distributed without blowouts. If a cut and fill format is used, a slit is made and a nozzle deposits filling into the cavity, then the surface is finished and allowed to set. Chocolate icing or other coatings are applied after glazing or instead of glazing depending on format. These coatings are typically fat-based and set by cooling rather than crystallizing like sugar glaze. Coating temperature and viscosity determine thickness and surface smoothness. Toppings are applied while the coating is tacky so they adhere before the surface sets. Packaging and handling are built to protect the glazed surface, which can mark easily. Donuts are typically loaded into cartons that prevent stacking pressure on the glaze. Carton loading uses guides that minimize contact with the top surface. If the product is individually wrapped, the donuts must be fully set and cooled to avoid condensation inside the wrap and to avoid smearing. Wrap films are selected to manage moisture because donuts dry out quickly if exposed to air. Snickers manufacturing can be understood from the cutter backward because the entire line is built to deliver a layered slab that is firm enough to slice cleanly, stable enough to ride through a chocolate curtain, and uniform enough that every bar finishes at the same weight. At the cutter, the slab must present a flat top surface, a consistent total thickness, and a predictable resistance to the knife. If the slab is too soft, caramel smears and drags, nuts dislodge, and edges tear. If the slab is too hard, the caramel fractures and the nougat can crack into ragged faces that later create coating voids. The plant therefore shapes and cools each layer, so the combined slab reaches a narrow cut window before portioning begins. The slab is built on a continuous belt. The bottom layer is aerated nougat. Nougat begins with two inputs that are prepared separately so they can be combined without collapsing the bubble structure. A cooked syrup that defines solids and elasticity, and a foam phase that carries metered air. Syrup cooking starts with sugar and glucose syrup streams that are metered into a cooker and concentrated. The cook endpoint sets the moisture level in the final nougat. A higher moisture syrup yields a softer nougat that can slump under the caramel layer. A lower moisture syrup yields a tighter nougat that becomes chewy and resists cutting. The cooker is operated to a precise endpoint, and the syrup is delivered forward at a controlled temperature so it strengthens foam but does not scorch it. The foam phase is produced from a protein solution. The solution is mixed to a defined concentration and fed to a continuous aerator. Air is metered in, and shear is applied to create small, uniform bubbles. Bubble size distribution matters because large bubbles collapse and create voids, while small bubbles create a smooth, light texture. Density is measured continuously because density is the direct control for nougat weight and bite. If density drifts, the finished bar weight drifts. Syrup and foam merge in a continuous mixer designed to fold rather than whip. Folding distributes syrup through foam without breaking bubbles. Syrup heat partially sets the protein films and locks the microcell structure. Fat is injected as a thin stream to soften bite and reduce stickiness. Emulsifiers can be added in small doses to stabilize the air-fat sugar system and improve flow at the depositor. The mixed nougat exits as a warm, aerated mass with controlled viscosity. Nougat is deposited onto the moving belt as a continuous slab. A spreader head lays down a wide band, and gauge rollers set thickness. Thickness control is critical because it defines the core height and influences later cooling time. The slab enters a cooling tunnel with staged zones. Early zones firm the surface enough to support caramel deposition. Later zones remove heat more gradually so the interior firms without forming a brittle skin. The target exit condition is a nougat slab that is firm but still receptive at the surface so caramel can bond. Caramel is prepared in a separate stream because it requires different cooking and different set behavior. Sugar and glucose syrup are cooked with dairy components to develop caramel notes and reach an elastic solids endpoint. The endpoint determines whether caramel behaves as a clean sheet or as a smear. Too low solids and caramel drags on knives. Too high solids and caramel fractures, especially when nuts create stress points. Fat is added to smooth the matrix and reduce tack. The caramel is cooled to a working temperature where viscosity is stable for deposition and held in jacketed tanks with gentle agitation to prevent skin formation. Peanuts are prepared as a topping stream that must spread evenly and remain dry. Roasted peanuts are screened to remove fines and broken pieces. Fines create dust and uneven coverage. Oversized pieces create peaks that cause thin chocolate spots later. The peanuts are cooled after roasting so they do not warm the caramel surface and change tack behavior. They are stored in dry conditions so they flow freely through spreaders. Layering begins when the nougat slab reaches the caramel station. Caramel is deposited as a continuous layer using a slot head. A leveling bar spreads it to uniform thickness. Temperature matching is essential. If caramel is too hot, it softens the nougat surface and creates a weak interface. If too cool, it does not fuse and can delaminate later. The line targets a condition where caramel wets the surface slightly and then begins to set as it moves forward. Immediately after caramel deposition, peanuts are applied. A spreader distributes nuts across the full width at a controlled mass flow. Distribution must be uniform. so every bar receives a similar nut density. A light pressing station can embed nuts slightly into caramel to improve mechanical lock. Pressing is controlled to avoid crushing nuts and to avoid squeezing caramel sideways, which would create thick edges and thin centers. After nut application, the slab enters a conditioning zone. This zone firms the caramel layer enough for cutting and locks nut position, so nuts do not slide when the slab is later accelerated. Cooling is staged to avoid differential contraction between nougat and caramel, because differential contraction can cause the slab to curl. Curling leads to uneven coating thickness and cutting errors. The slab is held flat by belt support and cooled to a target firmness. Edge trimming removes uneven edges where thickness variation is most common. Trim is collected for controlled rework streams. The main slab then enters lane cutting. Rotary knives slice the slab into long lanes of constant width. A crosscutter then slices lanes into bar lengths. Knife timing is synchronized to belt speed to maintain consistent weight. Knife surfaces are managed to reduce caramel buildup that would tear edges. Clean edges are important because ragged edges trap air under the chocolate curtain and cause voids. The cut bars are transferred to the enrobing line with controlled spacing. Spacing prevents chocolate bridges. Transfer points are designed with minimal drop height because impact can dislodge nuts and dent nougat. A brief pre-chill can be used to firm the surface and improve chocolate coverage. Pre-chill is balanced so the bars do not become so cold that condensation forms when they enter warmer chocolate equipment. Chocolate coating is prepared and held in a tempering loop. Chocolate is melted and filtered to remove unmelted fragments. Tempering creates a stable seed crystal population through controlled cooling and reheating. Working temperature is maintained tightly because viscosity defines curtain thickness and coat weight. Viscosity that drifts too high produces heavy coatings and thick feet. Viscosity that drifts too low produces thin coatings and exposed corners. Enrobing coats the bars with a top curtain and a bottoming system. The top curtain covers the top and sides. The bottoming system coats the underside, sealing the bar and protecting caramel from exposure. Excess chocolate drains through a wire belt. Air knives smooth the surface and control foot thickness. Air knife settings are tuned so they remove excess without exposing nut peaks at corners. If a top drizzle pattern is required, it is applied immediately after enrobing while the surface is still tacky. A stringer deposits thin lines that bond to the base coat. The bars then enter the cooling tunnel. Cooling is staged to set the chocolate and preserve surface quality. The first zone sets the surface quickly so the coating does not slump and nuts do not shift. Subsequent zones cool more gradually to promote stable cocoa butter crystals and reduce bloom risk. Tunnel humidity is controlled to prevent condensation that would cause sugar bloom and dullness. Bars exit the tunnel at a temperature suitable for wrapping with a coating hard enough to resist scuffing. After cooling, inspection checks coating coverage, shape, and weight. Vision systems detect exposed edges and coating voids. Weight checks confirm portion control across cutting and coating. Bars outside tolerance are diverted. Chocolate rework is remelted and returned upstream. Nougat and caramel rework is handled separately because their aeration and moisture differ from fresh streams. Wrapping begins once bars are fully set. Flow wrappers form film around each bar and seal it with controlled heat and dwell time. Film tension is controlled to avoid scuffing the coating. Coating is applied for traceability. Wrapped bars are collated into multi-packs or cartons, then case packed. Lay's-style potato chips are manufactured by controlling three things more tightly than anything else: slice geometry, surface starch, and oil temperature. When those three are stable, the process reliably turns raw potatoes into thin, brittle chips that drain cleanly accept seasoning evenly, and stay crisp inside a sealed bag. The line is easiest to follow from the seasoning drum backward because seasoning performance tells you whether the upstream steps produce the right surface. Chips that are too wet reject powder and clump. Chips that are too dry fracture into excessive fines. Chips that carry excess surface oil feel greasy and carry seasoning unevenly. The factory therefore builds chips so they exit the fryer with a narrow moisture and oil window before they ever reach flavor application. The final steps start at de-oiling. Chips exit the fryer on a mesh conveyor and immediately pass over vibrating drains. Vibration shakes off free oil while the chips are still hot and rigid enough to tolerate movement. Air knives or blowers can strip oil film from the surface and from curled edges. This is not a cosmetic step. Excess surface oil can cause seasoning to clump and can also migrate into the bag headspace, increasing the perception of greasiness. De-oiling settings are tuned so oil is removed without cracking the chips into fragments. From de-oiling, chips flow into a rotating seasoning drum. The drum provides gentle tumbling, so every chip surface is exposed. Seasoning is dosed as a fine powder or a blend and is metered by mass flow to match chip throughput. Adhesion relies on a thin oil film that remains on the chip surface. Too much film causes heavy seasoning pockets. Too little film yields bare chips. Drum speed and fill level are adjusted so chips roll rather than slide, because rolling distributes seasoning and minimizes breakage. A short dwell time allows seasoning to distribute fully without grinding chips into fines. Immediately after seasoning, chips move toward packaging, but they first pass through screening. Screens remove small fragments and fines produced by slicing and frying. Removing fines improves bag appearance and also prevents seals from being contaminated by dust. Fines also absorb more oil and can go stale faster, so their removal improves consistency. Packaging begins with portioning into bags using multi-head weighers. Chips are lightweight and irregular, so the weigher uses multiple small hoppers and selects combinations that hit target weight. Drop paths are designed to reduce breakage. Bags are formed from barrier film that resists oxygen and moisture transmission. Nitrogen flushing is commonly used to displace oxygen and to create headspace that cushions chips. The bag is sealed with heat and pressure. Seal parameters are tuned so seals hold without wrinkles that would leak. All of those downstream steps assume chips arrived with the correct structure, which is created in the fryer. Frying is not just cooking. It is a controlled dehydration process that forms a rigid, porous matrix. Chips enter hot oil and water at the surface flashes to steam. Steam leaves through the sliced surfaces, creating pores and crispness as moisture content drops. Oil temperature is held in a narrow band because it controls how fast water leaves and how much oil enters. If oil is too cool, chips stay in the fryer longer, absorb more oil, and remain flexible rather than crisp. If oil is too hot, the surface can brown before moisture leaves evenly, producing dark edges and fragile structure. Residence time in the fryer is controlled by conveyor speed and by chip bed depth. Bed depth matters because too deep a layer reduces oil contact and yields uneven color. Oil circulation is designed to keep temperature uniform across the fryer. Filters continuously remove crumbs and starch fragments that break off. Without filtration, crumbs burn and darken the oil, increasing dark specks and changing heat transfer. Oil turnover with fresh oil additions maintains consistent frying behavior over long runs. Before frying, slices go through a washing stage that controls surface starch. Freshly sliced potatoes release starch that forms a sticky film. If that film remains, slices stick together in the fryer and cook unevenly. The wash system uses flumes and sprays to remove free starch. Flow is tuned so slices separate without breaking. After washing, slices are dewatered on vibrating screens and with air knives. Removing surface water matters because water entering the fryer cools the oil locally and increases splatter and oil breakdown. Dewatering stabilizes fryer temperature and improves chip texture. Slice geometry is set at the slicer and influences every downstream step. Potatoes are fed into a high-speed slicer where a rotating blade cuts thin slices at a fixed thickness. Thickness is the primary determinant of crispness and color. Thinner slices cook faster and become very crisp, but can be fragile. Thicker slices cook slower and can remain slightly chewy if the fryer is not adjusted. The slicer uses sharp blades to create clean edges. Dull blades tear cells and create ragged surfaces that absorb more oil and shed more fragments. Many chip lines also apply slice sorting. A screen separates small fragments and slivers from full slices. Slivers fry faster and become darker, so removing them improves color consistency. Some lines also classify slices by thickness using optical measurement and divert out-of-range slices. Keeping thickness narrow allows fryer time and temperature to remain stable. The potato feed to the slicer is stabilized by upstream size grading. Potatoes arrive in bulk with variation in diameter and length. Large variations can cause feed surges and slicing inconsistency. A grader routes potatoes to appropriate lanes or rejects extremes. Feed hoppers and belts deliver a steady flow to the slicer, so blade load remains consistent. Consistent blade load produces consistent thickness. Raw potato preparation begins at receiving. Potatoes enter water flumes that transport them while removing stones and heavy debris in trap sections. Spray washers remove soil that would dull blades and discolor oil. Peeling is used on many lines. Abrasive peelers remove skin by rubbing against carborundum surfaces, while steam peeling can loosen skins quickly before mechanical removal. Peeling choice depends on product style. For classic thin chips, peeled potatoes provide uniform color and reduce dark spots. After peeling, potatoes are rinsed to remove peel fragments and then inspected by optical sorters that remove rotten spots and green areas that would fry dark and taste bitter. Temperature control begins early because potato temperature affects slicing and frying. Cold potatoes slice more cleanly and release less surface starch, but very cold potatoes can have higher reducing sugar levels from cold storage, which increases browning. The plant manages potato storage and tempering so raw potatoes arrive at a temperature that supports both slice quality and target color. Reducing sugar content is managed through raw material selection and sometimes through brief conditioning treatments. Potatoes with high reducing sugars brown too fast and produce dark chips. Wash and blanch steps are more common for fries than for chips, but some chip lines manage sugar through storage control and by blending lots. The goal is consistent color without relying on heavy downstream correction. After slicing and washing, the system focuses on gentle transport. Slices move through flumes and onto dewatering belts. The line avoids high drop heights because thin slices tear easily. Torn slices become fines and increase oil degradation in the fryer. Gentle transport reduces breakage and improves yield. The transition into the fryer is designed to avoid clumping. Slices are spread into a uniform layer before entering oil. Spreading can be done with distribution belts or vibratory feeders. A uniform entry layer ensures every slice sees similar oil contact and similar dwell time, producing uniform moisture removal and color. After frying, chips pass through a color sorting stage on many lines. Cameras measure chip color and eject overly dark chips with air jets. This stage compensates for occasional raw potato variability and fryer transient conditions. Sorting reduces the incidence of bitter dark chips in the bag and improves visual uniformity. Peanut butter production begins when raw peanuts enter a roaster and their pale centers start changing into the base of a smooth spread. The peanuts arrive as cleaned kernels, but they still need sorting before heat treatment. They move across vibrating screens that remove small fragments, dust, and oversized pieces. Air separators lift away light skins and loose material. Magnets remove tiny metal fragments before the nuts continue. The accepted peanuts feed into a continuous roaster. Inside, hot air moves through the peanut bed while the nuts travel forward on a belt or inside a rotating drum. The heat drives off moisture and develops the roasted texture needed for grinding. The peanuts darken slightly as they roast. Their internal oils become easier to release. The structure becomes more brittle, so the nuts will break cleanly in the grinder instead of smearing unevenly. Time and temperature are controlled closely because roasting affects color, flavor, texture, and final appearance. The hot peanuts exit the roaster and enter a cooling section. Air pulls heat away rapidly. Cooling stops the roasting action and prevents the nuts from continuing to darken after leaving the oven. The peanuts must reach a stable temperature before the next step. After cooling, the peanuts move into blanching. The thin reddish-brown skins are loosened and removed. Blanching equipment may use gentle abrasion, heated surfaces, or air movement to separate the skins from the kernels. The skins break away as the peanuts rub against rollers or belts. Airflow carries the light skins out of the product stream. The blanched peanuts are now pale, clean, and ready for final inspection. Any remaining dark spots, damaged nuts, or off-color kernels can be removed by optical sorting. Cameras examine the moving peanuts and eject unacceptable pieces with short bursts of air. The sorted peanuts move toward grinding. This is where the solid nut becomes paste. The first grinder cracks the peanuts into coarse particles. Rotating plates or toothed surfaces crush the kernels. Oil begins to release from the peanut cells. The dry nut pieces quickly become a thick, rough paste. The coarse paste passes into a second grinder. The particles become smaller and more oil is released. The mixture grows smoother and more fluid. The paste changes from chunky grit into a heavy flowing mass. For smooth peanut butter, the grinding continues until the particle size reaches a fine range. The texture must be creamy but still dense. If particles remain too large, the spread feels gritty. If the grinding is too aggressive, the paste can overheat and change consistency. For crunchy peanut butter, a portion of peanuts follows a separate chopping path. These peanuts are roasted, blanched, and cut into controlled pieces rather than ground completely. Screens separate the chopped nuts by size. Fine powder and oversized pieces are removed. The accepted peanut granules are stored separately until they are folded into the smooth base. The ground peanut paste enters a mixing tank. Salt is added in a measured amount. Sweetener may be added depending on the formula. Stabilizing fat or emulsifying ingredients may also be added to reduce oil separation and improve spreadability. The mixer works slowly but powerfully. Peanut paste is thick, so the agitator must move heavy material without whipping in too much air. The blades fold the ingredients through the paste until every portion has the same salt level, sweetness, and consistency. Stabilizers are important in many commercial peanut butters. Natural peanut oil can separate and rise to the surface during storage. Stabilizing ingredients help hold the oil within the paste structure. The mixture becomes more uniform and less likely to form a liquid layer at the top of the jar. The paste may be heated slightly during mixing to improve flow. Warm peanut butter moves more easily through pipes and fillers. The temperature is controlled because too much heat can affect texture and flavor. For crunchy peanut butter, chopped peanut pieces are added after the smooth base is fully mixed. A gentle blending system folds the granules through the paste. The movement must be strong enough to distribute them evenly, but not so rough that the pieces break down into dust. The peanut butter then passes through a deaeration stage. Grinding and mixing can trap small air bubbles inside the thick paste. In a vacuum chamber, reduced pressure pulls air from the product. Bubbles expand, rise, and collapse. The paste becomes denser and smoother. Deaeration helps the filling process. A paste with trapped air can create inconsistent jar weights and visible pockets. Removing air gives the peanut butter a more solid, continuous appearance when filled. The finished peanut butter moves into a holding tank above the filling line. The tank may be jacketed to maintain temperature. Slow agitation keeps the product uniform without damaging texture. From here, pumps send the spread toward the filler. Jars are prepared on a separate packaging line. Plastic or glass containers arrive empty and are organized by an unscrambler or depalletizer. They move into single-file lanes on a conveyor. Before filling, the jars may pass through an air rinser. Each jar is inverted or positioned under a nozzle. Filtered air removes loose particles from the interior. The jar returns upright and continues toward the filling station. The filler is designed for thick product. Peanut butter does not pour like water. It stretches and holds shape. Piston fillers, rotary positive displacement fillers, or servo-controlled pumps measure each portion and push it through wide nozzles. The nozzle lowers toward the jar opening. Peanut butter enters as a dense ribbon, folding into the bottom and rising steadily. The filling speed must prevent air pockets while keeping the jar rim clean. As the level rises, the nozzle may lift to stay just above the product surface. When the correct weight or volume is reached, the valve closes. A cutoff action stops the thick stream cleanly. Some nozzles use a brief reverse pull to prevent strings of peanut butter from trailing across the rim. Filled jars move to the leveling or settling section. A short vibration or controlled movement can help the surface flatten slightly. The top remains thick and matte with a slow settling texture rather than a liquid surface. The jars then enter the capping area. Caps are fed from bulk hoppers into sorting bowls. The sorter orients each cap and sends it down a chute to the capping heads. Before the cap is applied, some jars receive an inner seal. A foil liner may be positioned over the mouth or built into the cap. When induction sealing is used, the capped jar passes beneath an induction head. Electromagnetic energy heats the foil layer and bonds it to the jar rim. The capper places a cap on each jar and tightens it to a controlled torque. Too little torque can create a weak seal. Too much can damage the cap threads or make the package difficult to open. The machine repeats the same tightening motion across every jar. After sealing, the jars pass through inspection. Check weighers verify the filled amount. Vision systems check cap presence, cap angle, jar shape, fill appearance, and possible product on the rim. Any defective jar is rejected automatically. If product residue appears on the outside, jars may pass through a cleaning station. Wipers or air jets remove smears from the surface. Clean jars move more smoothly through labeling equipment and case packing. Labels are applied next. Round jars pass through wraparound labelers. A pressure-sensitive label peels from a backing web and attaches to the jar side. Rollers spin the jar and press the label smoothly around the curve. A high-volume Dunkin' Donuts line is built around delivering dough or batter to hot oil in the same condition every minute, because frying fixes shape, crumb, and surface in seconds and leaves little opportunity to correct variation downstream. Ingredient conditioning starts the process. Flour is sieved to remove lumps and aerated for consistent hydration. Sugar is screened so crystal size stays stable and dissolves predictably in mixers. Salt and leavening are pre-blended, so distribution is uniform at low inclusion rates. Fats are tempered so their plasticity is consistent for dough systems or melted and cooled to a target temperature for batter systems. Eggs and dairy liquids are tempered because small temperature shifts change emulsion behavior and batter viscosity. Water temperature is selected to land the final dough or batter in a narrow temperature window. For yeast-raised donuts, the front end is a developed dough that must proof consistently. Flour enters a mixer and is hydrated with water and dairy liquids, while yeast is dispersed early, so fermentation is uniform. Mixing begins slowly to hydrate without dusting, then increases speed to develop gluten. Gluten development is tuned to a target elasticity that can trap gas but still sheet cleanly. Fat is added after initial gluten formation, so it softens the network without blocking development. Eggs and emulsifiers are incorporated in a controlled sequence, so they form a stable dispersion inside the dough rather than separating into streaks. Dough temperature is managed as a primary control variable. Mixing friction generates heat, so water temperature and mix time are adjusted to reach a target dough exit temperature. That exit temperature controls dough stiffness and yeast activity. The dough then enters a timed rest, where moisture equalizes and gluten relaxes. Relaxation reduces snapback in sheeting and improves cut accuracy, while early fermentation begins creating fine gas cells without fully expanding the dough. The rested dough feeds a divider and sheeter. Dividing stabilizes feed rate into rollers, so thickness remains steady across time. Sheeting reduces thickness through several roller gaps rather than one large reduction to avoid stress lines that later become weak points in the fryer. Gauge rollers lock the final sheet thickness, which becomes a main determinant of donut weight and final crumb thickness. Rotary cutters punch rings at line speed, cutting an outer diameter and removing the center plug. Cutter sharpness matters because dull edges compress the dough and create ragged rims that absorb more oil and brown unevenly. Scrap around the cutouts is lifted and returned to the dough stream at controlled ratios, because high scrap ratios increase working and shift gluten development. Cut rings move into proofing, where the dough expands to near final volume. Proofing is run at controlled temperature and humidity. Temperature sets yeast gas production rate, and humidity prevents a dry skin that would restrict expansion and cause blowouts. Proof time is tuned to reach a target volume and cell structure. Underproof yields dense donuts with limited lift. Overproof yields fragile donuts that collapse when moved or flipped in oil. For cake-style donuts, the line works with a chemically leavened batter rather than a fermented dough, so the objective is minimal gluten with uniform leavening dispersion. Dry ingredients are pre-blended, so chemical leavening and salt are evenly distributed. Liquid ingredients are blended separately, so eggs and fats emulsify before meeting flour. The streams combine and mix only long enough to hydrate flour and remove lumps, because overmixing develops gluten and produces tough donuts with irregular cracking. Batter temperature is held tightly because viscosity must remain stable for depositing. If batter is too thin, it spreads and loses ring definition when it hits oil. If too thick, it deposits unevenly and can trap air pockets that create voids. Depositing forms rings directly into the fryer for cake products. A depositor meters batter through shaped nozzles with timing synchronized to the fryer conveyor, so spacing is consistent. Deposit weight is controlled by pump stroke or timed flow. The batter must release cleanly from the nozzle and hold its shape long enough for the surface to set in oil. Frying is the setting step for both routes. Oil temperature, dwell time, and turnover are the controlling variables. When a donut enters oil, surface water flashes to steam, creating outward pressure that expands the structure and delays oil penetration during the earliest phase. Starch gelatinizes at the surface and forms a crust. Proteins coagulate and lock the structure. Browning reactions accelerate as the surface dries, creating the final color and flavor profile of the crust. Yeast-raised rings usually float and fry on one side first. Conveyor speed determines how long the first side sets before a turning mechanism flips the donut. Flip timing is critical. Flipping too early deforms the ring and creates flat spots. Flipping too late creates an overly thick crust on one side and uneven color. The second side fry completes structure set and balances moisture loss so the donut does not warp. Cake donuts set more quickly because the batter begins as a suspension with chemical gas release and rapid heat penetration. Fry conditions are tuned so the surface sets at the right moment. If the surface sets too fast, expanding gases crack the crust and create blowouts. If the surface sets too slowly, the batter spreads and forms misshapes. Residence time and temperature are adjusted together to manage this balance. Oil management runs continuously because crumb fragments and batter fines burn and darken the oil, changing heat, transfer, and color development. Filtration removes fines and keeps the oil clean. Oil is circulated to maintain uniform temperature across the fryer width and prevent striping. Controlled oil turnover keeps frying behavior stable, so the same dwell time produces the same color and oil pickup. As donuts exit the fryer, surface oil is removed immediately. Drain belts and vibrating conveyors shake off free oil, and air blowers strip oil from creases. This step is important because surface oil interferes with glaze adhesion and increases greasy feel. The donuts then enter cooling, where internal steam condenses, fats begin to crystallize, and the crumb firms. Cooling is staged to stabilize structure and prepare for finishing. Hot donuts are soft because fats are liquid and the crust is still plastic. As they cool, the crust becomes rigid and the interior moisture redistributes. Cooling airflow is controlled so the surface does not dry too fast, which would create a tough crust that flakes under glaze. Cooling also prevents packing too warm, because warm donuts release moisture into packages and soften coatings. Glazing and icing are applied in controlled viscosity windows. A classic sugar glaze is mixed to a defined solids level and held warm enough to flow as a thin film. Donuts pass under a glaze curtain or are dipped, and the excess drains as they travel on a setting conveyor. As water evaporates, the glaze crystallizes into a smooth shell. Chocolate or fat-based icings are heated to a target flow temperature and applied by curtain or dipping, then set by cooling so the fat network solidifies without cracking. Powdered sugar or cinnamon sugar finishes are applied while the donut surface still has slight warmth and tack. The donuts pass through a shower or drum that distributes powder evenly, and screens recover excess. Toppings are applied during the short tack window before coating set. Feeders meter sprinkles or nut pieces at a rate synchronized to belt speed, so coverage stays uniform without clumps. Filled donuts at an injection step after cooling reaches a firm but pliable state. Fillings are prepared to a pumpable viscosity that holds shape without leaking. Multi-needle injectors penetrate at controlled depth, and piston strokes deliver consistent doses. Needle retraction timing is coordinated to reduce backflow and surface smearing. If a side fill format is used, a controlled slit is cut, and a nozzle deposits filling into the pocket. Then the product passes through a brief set zone so the filling surface stabilizes. Packaging is designed around protecting finishes and managing moisture exchange. Donuts intended to stay soft use barrier materials that reduce moisture loss. Donuts with a crisp shell need packs that prevent moisture gain that would soften crust and glaze. Cartons and clamshells protect toppings from abrasion and reduce contact marks, while flow wrap provides strong moisture control but requires the surface to be fully set to avoid smearing. Seal temperature and dwell are tuned so seals close without heating the donut enough to soften coatings. A Chick-fil-A style breaded chicken fillet is produced by turning trimmed poultry breast into uniform portions. conditioning the meat so it stays juicy after cooking, applying a controlled flour and batter system that bonds tightly, setting the coating quickly in hot oil, then chilling and packaging so every fillet reheats with the same crust and bite. Production starts with raw poultry arriving chilled and moving into size reduction and standardization. Breast meat is trimmed to remove thin tails and ragged edges that would overcook and create hard spots. The trimmed pieces are sorted by weight band so the forming line can hold a tight portion range. Consistent portion mass is a core control because fry time and internal temperature rise rate depend on thickness. The meat is then conditioned to stabilize moisture, retention, and texture. A measured solution is prepared from water, salt, and functional ingredients that improve binding and reduce purge. This solution is mixed to a defined concentration and held cold so it does not warm the meat. The solution is introduced to the meat by tumbling or by injection followed by tumbling. Tumbling cycles alternate between rotation and rest so the solution distributes through muscle fibers without tearing them. Vacuum tumbling is often used because removing trapped air improves uptake consistency and reduces voids that can appear as soft pockets after cooking. The endpoint is judged by pickup percentage and by uniform surface tack rather than by extended mixing time. Once conditioned, the meat is portioned into fillet shapes. If whole muscle fillets are used, they are pressed to a consistent thickness using calibrated rollers. Pressing is gentle and aims to widen and even the piece without shredding. Thickness control matters because a thick center can remain undercooked when the crust looks done. If formed fillets are used, the meat is ground coarsely and then shaped in a forming machine. But a classic sandwich fillet format typically relies on whole muscle thickness control rather than full comminution. After shaping, the fillets pass through a brief chill stage. Chilling firms the surface proteins and improves handling so the pieces do not smear when they enter the coating system. Chilling also stabilizes the pickup behavior of the next layers because warmer surfaces thin the batter and increase coating variability. The coating system is built as a multi-step adhesion stack. The first layer is a pre-dust, usually a seasoned flour blend that absorbs surface moisture and creates a dry interface. Pre-dust is delivered as a curtain or bed where fillets tumble and roll so all surfaces are covered. Excess pre-dust is removed by gentle shaking because too much dry flour creates thick patches that later detach. After pre-dust, the fillets enter a batter stage. The batter is mixed in tanks that maintain solid suspension and viscosity. Viscosity is monitored because it determines coating thickness and how the batter bridges surface contours. Batter temperature is controlled because warm batter flows too thin and produces weak coating, while cold batter thickens and creates ridges. The fillets pass through a batter waterfall or immersion where every surface is wetted. Air knives can remove excess and set a uniform film thickness. Breading follows immediately while the batter is still wet. Breading is usually a seasoned flour system with a defined particle size distribution. Some formats use a mix of fine flour and larger crumb to create a textured crust. The fillets travel through a bed of breading while top belts press lightly to embed particles. This compression step is critical because it turns loose surface flour into a mechanically locked layer that will survive frying and later handling. Excess breading is removed so the crust is thick but not clumpy. If the target crust requires a distinctive craggy surface, the line can use a second batter and breading pass. The first pass builds the base and the second pass builds height and texture. Each pass is tuned so the coating does not become so heavy that it insulates the meat and slows cooking. After breading, the fillets enter a short setting zone before frying. This can be a brief rest on a belt that allows the batter to hydrate the dry breading and form a cohesive paste at the interface. hydration improves adhesion and reduces blow-off in the fryer. The rest time is short because the coating must not become wet enough to smear. Frying is the structure-setting step. Fillets enter a continuous fryer where oil temperature and dwell time are tightly controlled. The fillets are held under oil by a top belt so they cook evenly and do not float and curl. As the fillet enters oil, surface water flashes to steam. That steam creates outward pressure that expands the coating slightly and forms pores. Starches in the batter gelatinize and then begin to dry into a rigid network. Proteins in the batter coagulate and lock the crust shape. Oil temperature is chosen to set the crust quickly while allowing heat to penetrate the meat at a controlled rate. If oil is too hot, the crust darkens before the center reaches the target internal temperature. If oil is too cool, the crust sets slowly, absorbs more oil, and becomes heavy. Dwell time is set by belt speed and fryer length. Bed loading is controlled because overcrowding reduces oil circulation and causes uneven color. Oil management runs continuously because breading fragments break off and will burn if not removed. Filtration systems remove fines and keep the oil clean. Circulation keeps temperature uniform across the fryer width. Fresh oil makeup maintains quality so heat transfer and browning stay consistent. At fryer exit, surface oil is removed by vibration and air stripping. Removing surface oil reduces greasiness and improves how the fillets package and reheat. The fillets then enter a cooling stage. Cooling stabilizes the crust and lets internal steam pressure fall gradually. If cooling is too fast, the crust can contract and separate slightly. If cooling is too slow, residual heat can soften the coating and reduce crispness. From here, the process can diverge depending on distribution format. For a chilled product, the fillets are cooled rapidly to a target core temperature and held under controlled conditions. For a frozen product, the fillets enter an individual quick freezer. The freezer uses high-velocity cold air to freeze quickly and preserve crust porosity. Rapid freezing forms smaller ice crystals and reduces moisture migration that would soften the crust later. The pieces are spaced so they freeze individually and do not stick. After freezing, the fillets are screened and inspected. Broken coating fragments are removed because they increase crumbs in the package and can burn during reheating. Size and weight checks confirm portion control. Optical systems can reject misshapes and incomplete coating. Metal detection can be placed after freezing when product flow is stable. Packaging begins with portioning. Multi-head weighers or counting systems assemble target weights for bags or cases. Drop heights are minimized because frozen breading can chip and create fines. Bags are formed from barrier film that limits moisture exchange. Moisture control is crucial because the crust will lose crisp potential if it picks up moisture in storage. Seals are made with controlled heat so the film closes without wrinkles. Seal areas must remain clean because crumbs can interfere with seal integrity. For food service formats, the fillets are packed into lined cases with internal bags. Case fill patterns are chosen to reduce compression on lower layers. Cases are sealed and coated. Pallet stacking is designed to avoid crushing that would fracture crust. Storage temperature stability prevents freeze-thaw cycles that create ice crystals on the crust and degrade reheating performance. The final product performance is engineered into the factory steps. Meat conditioning sets moisture retention, so the fillet stays juicy after a high heat finish. Pre-dust and batter create a bonded interface so the crust does not slide off when bitten. Breading particle size and compression set the surface texture. Fry temperature sets pore structure and crust rigidity. Cooling and freezing preserve that structure. Packaging maintains low moisture exchange so the crust can crisp again during final cooking or reheating. A McDonald's-style hamburger is manufactured by turning beef trim into uniform patties that cook the same way every time, producing buns that stay soft yet resilient after freezing and toasting, then portioning and packaging each component so it can be assembled rapidly with consistent texture. Beef patty production starts with raw trim selection and temperature control because fat level and grind behavior determine bite and shrink. Beef arrives as chilled trim in defined lean to fat bands. The trim is inspected for hard connective pieces that would create tough spots and for excessive surface fat that would smear during grinding. Trim is kept cold from the start because warm fat smears into a paste, which causes dense patties and poor cook texture. The trim enters a coarse grinding stage first. Coarse grinding breaks the meat into uniform chunks without turning it into an emulsion. This is done through a grinder plate with larger holes, so particle definition is preserved. The coarse ground meat then moves to blending, where multiple trim lots are combined to hit a target fat percentage. Blending uses paddles that fold the meat rather than whip it, because air incorporation and overworking change density and can create voids. After blending, the meat is ground again through a finer plate to create the target particle size distribution. Particle size affects how the patty binds and how it releases juices. Too coarse yields a crumbly patty that breaks at the edges. Too fine yields a tight, rubbery bite. Grind temperature is monitored continuously because friction can warm the meat. If temperature rises, the line slows or adds colder meat to keep the mix in range. The blended grind is moved quickly to forming. Forming turns the loose ground meat into patties with a fixed diameter, thickness, and mass. A patty former meters meat into a cavity and compresses it to a set density. Compression must be strong enough to make the patty hold together during freezing and handling. Compression must not be so strong that the patty becomes dense and loses its characteristic bite. Formers often imprint a pattern on the surface. The imprint increases surface area and helps heat penetrate evenly during cooking. Weight control is enforced at the forming head. Portioning is measured by volume with density control or by mass flow with feedback. Tight weight control is important because cook time is fixed in high volume systems, so patties must reach target internal temperature within the same dwell. Patty thickness control is equally critical because a thicker patty heats slower and will be underdone when a thinner one is correct. Immediately after forming, patties enter a rapid freezing step. Freezing locks the shape and prevents patties from sticking together. Individual quick freezing is used with high velocity cold air. The patties travel on a belt through a tunnel where cold air freezes the surface quickly first, then drives the core down to the target temperature. Rapid freezing forms smaller ice crystals and preserves texture better than slow freezing, which can create larger crystals that damage muscle structure. Patties are then separated, counted, and stacked into interleaved layers. Interleaving uses paper or film sheets between patties to prevent adhesion and simplify later separation. Stacking pressure is controlled so patties do not deform. The stacks are bagged or boxed in a way that limits moisture exchange and protects edges from chipping. Metal detection and weight verification typically occur after freezing when product flow is stable and consistent. The bun is produced on a separate bakery line, built around controlling softness, resilience, and freeze-thaw stability. Flour is sieved and blended to a target protein range because gluten strength controls how the bun holds up to toasting and compression. Sugar and salt are metered precisely. Yeast is staged as a controlled addition because fermentation rate must match line speed. Fats and emulsifiers are included to soften crumb and extend softness after freezing. Water temperature is controlled because dough temperature drives fermentation speed and dough handling. Mixing develops gluten to a defined endpoint. The dough must be strong enough to trap gas and rise, but not so strong that the bun becomes chewy or tough. Mixing begins with hydration and then transitions into higher energy kneading until the dough reaches a smooth, elastic state. Dough temperature is checked at discharge because mixer friction can warm the dough and accelerate fermentation. If dough exits too warm, proof times shorten and the process becomes unstable. After mixing, dough is rested and then divided. Dividers. Portion dough into equal pieces by weight. Portion weight directly determines bun diameter and height. Divided pieces are rounded to create surface tension, which supports a uniform shape during proofing. Rounded dough balls then rest briefly to relax so they can be shaped without tearing. Shaping forms the final bun geometry. Dough balls are flattened slightly and placed onto baking trays or oven bands. Proofing follows in a warm, humid environment. Proof temperature controls yeast activity and gas generation. Humidity prevents skin formation, so the bun can expand smoothly. Proof time is tuned, so buns reach a target volume and internal cell structure. Underproof yields dense buns with low softness. Overproof yields weak buns that collapse and wrinkle. Baking sets structure and dries the bun to a controlled moisture endpoint. Tunnel ovens run zoned heat, so the surface sets and the crumb cooks without excessive crust hardness. Early oven zones drive oven spring as trapped gas expands. Mid zones gelatinize starch and coagulate proteins to fix the crumb. Later zones develop a light crust color and finish internal moisture reduction. The bun must not be too dry because it will feel stale. It must not be too wet because it will collapse and compress poorly. After baking, buns cool on conveyors with controlled airflow. Cooling sets the crumb as fats crystallize and moisture redistributes. Slicing is done after cooling reaches the right firmness. Slicers cut buns horizontally with blades that maintain a consistent hinge or full separation depending on format. Slice depth is controlled because it affects later toasting behavior and bun strength during assembly. Sesame seeding, if used, is applied either before baking for adhesion or after with an adhesive wash depending on equipment design. For high volume distribution, buns are often frozen. Freezing protects softness and allows stable inventory. Buns enter a freezing tunnel where surface is frozen quickly to maintain shape. Packaging then seals buns in bags with barrier properties that limit dehydration. Bag seals must be strong because freezer burn dries bun surfaces and changes toasting behavior. Cheese slices, pickles, onions, and sauces are produced as separate streams with their own controls. But in the context of assembly readiness, the main requirement is portion uniformity and stable handling. Cheese is portioned into slices with tight thickness. Pickles are cut to consistent thickness, so acidity and crunch are predictable per unit. Dehydrated onions are produced by slicing onions and drying them to a low moisture level, then sizing flakes, so rehydration in the final product is consistent. Sauces are mixed as emulsions with defined viscosity, so dispensing systems deliver repeatable weights. Packaging and logistics are treated as part of the production system because the end product depends on thaw and cook behavior. Frozen patties are boxed in counts that match downstream loading systems. Boxes are designed to stack without crushing product. Buns are packaged to reduce moisture loss and protect shape. Temperature stability through storage is critical because freeze-thaw cycles create ice crystals that damage texture and cause condensation inside packs. The final operational transformation happens at the cooking line, where frozen patties are separated and cooked on a clamshell grill. The clamshell grill is engineered for repeatability. Patties are loaded onto a lower hot platen and then a top platen closes to contact both sides. Contact cooking on both sides reduces cook time and ensures uniform heat penetration. Time and platen temperature are fixed, which is why patty thickness and mass upstream must be consistent. The surface imprint on the patty increases contact and helps fat render evenly. The first movement for sardines is washing. Fresh or chilled sardines pass through rotating drums and spray channels where cold water removes loose scales, blood, and surface debris. The fish slide against stainless steel guides, turning and flashing under the water as the line separates clumps and spreads them into a steady flow. Their bodies are still whole at this point, but the factory is preparing them for a much tighter transformation. Sizing comes next. The sardines travel across grading equipment with slots, rollers, or vibrating channels that separate them by length and thickness. A can needs fish of similar size so the pieces pack evenly and cook uniformly. Fish that are too large move to another format. Smaller fish may go to a different can size or product style. Now the line begins shaping the fish for the can. The sardines move into heading and gutting equipment. Blades or cutting wheels remove the heads. A mechanical opening system cuts the belly area and removes the internal contents. Water jets rinse the cavity immediately after cutting. The fish are no longer whole. They have become prepared bodies with clean interiors and trimmed ends. The trimming must be consistent. If too much is removed, the yield and shape are poor. If too little is removed, the fish will not pack cleanly. The machine holds the fish in channels and guides them through the blades, so every body leaves at a similar length. The cleaned sardines pass through another rinse. Water flushes away loose fragments and leaves the fish ready for salting or brining. The surface becomes cleaner and firmer. What happens next controls both texture and flavor before the fish ever reaches the can. The sardines enter a brining stage. They move through a saltwater bath or receive a controlled salt treatment. Salt begins drawing moisture from the surface and seasoning the flesh. The brine concentration and contact time must be balanced. Too little salt leaves the fish bland and soft. Too much makes the flesh harsh and dry. After brining, the sardines drain on perforated belts. Excess liquid falls away. The bodies are now slightly firmer. Their surface is ready for the first major heat step. Some canning lines pre-cook the sardines before packing. The fish pass through a steam cooker or continuous oven. Steam surrounds them, and heat moves into the flesh. The texture changes from translucent raw fish to opaque, firm cooked fish. Moisture and natural oils release from the tissue. This stage is one of the hidden turning points. If the sardines are packed raw without the correct process, too much liquid can release later inside the can. If they are pre-cooked too aggressively, the flesh becomes dry and breaks during packing. The cooker gives the fish enough firmness to handle while preserving the soft structure needed in the final can. The cooked sardines move through cooling and draining. Fans or controlled air reduce surface heat. Perforated conveyors let liquid drain away. The fish must be cool and stable enough to enter the packing station without tearing apart. Now the cans enter the process from a separate path. Empty metal cans feed from stacks or bulk depalletized trays. They move along conveyors toward cleaning and inspection. The cans are open at the top, with rolled rims ready for sealing later. Air jets remove loose particles from the interior. Guides align the cans so they arrive beneath the packing equipment in a steady rhythm. The sardines and empty cans meet at the filling section. The fish are arranged by orientation. Some lines pack them by hand-like mechanical placement, using guides and portioning devices. Other systems use semi-automatic feeders that align the fish and slide them into the can. The goal is a tight, neat arrangement with the fish lying flat or slightly nested. The packing pattern depends on the can style. In rectangular cans, sardines may be laid side by side with alternating head and tail ends to use the space efficiently. In round cans, smaller fish may curve slightly around the container. The metal walls define the final block of fish. This is where the product starts looking familiar. The fish are no longer just moving along a belt. They are becoming a compact portion inside a shallow metal container. After the fish are placed, liquid is added. The filling medium may be oil, tomato sauce, water, brine, mustard sauce, or another prepared sauce. Each liquid has its own preparation system. For oil-packed sardines, filtered oil is held in a stainless steel tank and pumped to the filler. The oil flows through nozzles into each can, filling the spaces between fish. It coats the surface and displaces air pockets. The oil level must be precise because too little leaves exposed fish, while too much interferes with sealing. For tomato sauce, a separate sauce line prepares the liquid. Tomato concentrate, water, salt, spices, and other ingredients blend in heated tanks. Agitators keep the sauce uniform. The sauce may pass through screens to remove oversized particles before filling. It must be thick enough to cling to the fish, but fluid enough to flow through nozzles. For brine-packed sardines, salt water is mixed to a controlled concentration. The brine fills the can around the fish and helps distribute seasoning through the pack. The brine must be clear, measured, and free from undissolved crystals. The liquid filler doses every can. Nozzles lower or position above the can opening and release the correct volume. The liquid creeps between fish bodies, filling narrow gaps. Air bubbles rise to the surface. The can now contains fish and medium, but it is not yet safe as a sealed product. The next stage traps the contents permanently. Before sealing, the can may pass through an exhaust or vacuum step. The goal is to remove excess air from the headspace. Heat or vacuum reduces trapped oxygen and prepares the container for a strong internal vacuum after processing. This helps the can maintain shape and reduces unwanted pressure changes during retorting. A lid is placed onto each filled can. The lid feeds from a magazine, separates one at a time, and drops onto the can body. The filled can enters the seamer. The seaming chuck holds the lid while rollers move against the rim. The first seaming operation curls the lid edge and can flange together. The second operation compresses the folds into a tight double seam. This seam is purely mechanical. Layers of metal interlock around the can edge, creating a sealed container that can withstand the heat and pressure of sterilization. Now, the most important transformation happens out of sight. The sealed cans move into retorts. These are large pressure vessels or continuous sterilizing systems designed to heat sealed cans to a controlled temperature for a controlled time. Steam, hot water, or a steam-air mixture surrounds the cans. Pressure prevents the containers from deforming while the internal contents heat. Inside each can, the sardines continue cooking. The fish soften, bones become tender. Oil or sauce moves into the spaces between the pieces. The liquid and fish exchange flavor. The can becomes a sealed cooking chamber, and the product develops its final texture. The retort cycle must be exact. Heat must penetrate to the coldest point inside the can. That point takes the longest to reach the target temperature. Time, temperature, can size, fill weight, liquid type, and product density all affect the thermal process. The system records the cycle, so each batch receives the required heat treatment. After sterilization, the cans are cooled under controlled conditions. Cold water or cooling media remove heat from the metal and product. Pressure control during cooling prevents the cans from bulging or drawing in too sharply. The contents stabilize as the temperature drops. Honey production begins when sealed honeycomb frames enter an uncapping machine and the thin wax layer over each cell is sliced away. The comb is already filled with thick honey, but the honey is trapped inside thousands of small hexagonal cells. Each cell is closed with a pale wax cap. Before extraction can begin, these caps must be removed without crushing the comb structure beneath them. The frames move between heated blades, vibrating knives, or rotating uncapping rollers. The wax surface breaks open in long strips. The exposed cells glisten as honey appears across the comb face. Cut wax falls away into a collection trough, carrying small amounts of honey with it. The uncapped frames then move into an extractor. This machine uses centrifugal force. Frames are loaded into a rotating basket or drum. When the drum spins, honey is flung from the open cells toward the outer wall of the extractor. At first, the honey leaves the comb in thick threads. As rotation increases, the streams become faster and heavier. The honey strikes the extractor wall and runs downward into a collection sump. The comb remains inside the frame, emptied but still shaped. The extractor speed is controlled. If it spins too slowly, too much honey remains in the cells. If it spins too aggressively, the wax comb can tear apart. The machine gradually increases speed, so honey leaves cleanly while the comb structure stays intact. The raw extracted honey flows from the base of the extractor into a coarse straining system. This first separation removes larger wax pieces, broken comb fragments, and other visible solids. The honey passes through screens, while heavier wax particles are held back. The uncapping wax collected earlier follows its own recovery path. Wax and honey move into a heated draining tank or wax separator. Gentle warmth softens the mixture and allows honey to drain away from the wax. The recovered honey joins the main stream after straining, while the wax is separated from the liquid process. The strained honey is still not ready for bottling. It contains tiny air bubbles, fine wax particles, and natural suspended material. It moves into a settling tank, usually a tall stainless steel vessel with a conical or sloped bottom. Inside the tank, time and gravity begin sorting the honey. Air bubbles rise slowly because honey is dense and viscous. Fine wax particles float upward. Heavier particles settle downward. The clearer honey remains in the middle zone of the tank. The settling tank may be gently warmed. Heat lowers viscosity, helping bubbles rise and making the honey easier to pump. The temperature is controlled carefully. The goal is not to cook the honey. The goal is to make it flow smoothly through pipes, filters, and filling valves. After settling, honey is drawn from an outlet positioned above the bottom sediment layer and below the floating foam layer. This avoids pulling in either settled material or surface scum. The stream moves toward finer filtration. Filtration can use mesh screens, cloth filters, or cartridge systems, depending on the desired clarity. The honey moves slowly because of its thickness. Pumps push it under controlled pressure through filter media that catch tiny wax particles and fine solids. The filter must be matched to the product style. A very fine filter produces clearer honey. A coarser filter leaves more natural material in the liquid. In either case, the process is designed to create a smooth, clean honey stream that can pass through filling equipment without clogging. The filtered honey enters a holding tank. This tank acts as a buffer between extraction and packaging. It keeps a stable supply ready for the filling line. The tank may include a slow agitator that turns gently, preventing temperature layers without whipping air into the honey. Honey from different extraction batches may be blended to create a consistent color, moisture level, and flavor profile. Blending is done inside large tanks. One batch may be darker and stronger. Another may be lighter and milder. Metered additions allow the final tank to reach the target specification. The blending motion is slow because honey traps air easily. A fast agitator would create bubbles that take a long time to escape. The paddles move gradually, folding the honey through itself in thick, slow currents. Moisture control is important in honey processing. Honey with too much moisture can become unstable. In a factory setting, moisture is checked before filling. If the honey needs adjustment, it may pass through controlled warming and evaporation equipment designed to reduce excess water without burning or darkening the product. The honey now moves toward the filling line. It is still warm enough to flow, but thick enough to hold its dense texture. Jacketed pipes may maintain temperature, so the honey does not cool and slow inside the line. Containers are prepared separately. Glass jars, plastic squeeze bottles, or rigid plastic tubs arrive empty and are fed into the packaging system. They move through unscramblers or depalletizers that organize them into single-file rows. Plastic squeeze bottles may be blow molded in a separate operation before arriving at the filling line. In that process, plastic is formed into bottles with flexible walls and precise neck finishes. The bottle must be strong enough to stand upright, but soft enough for squeezing. Before filling, containers pass through cleaning or air rinsing equipment. Each container is inverted or positioned under a nozzle. Filtered air removes dust or loose particles from the interior. The container returns upright and enters the filler. The honey filler is designed for viscous liquid. It does not behave like a water filler. Honey stretches, clings, and forms threads when the nozzle stops. The machine must dose accurately while preventing drips across the container rim. Piston fillers, gear pumps, or servo-controlled volumetric fillers are common for thick products. A measured volume of honey is drawn into a chamber, then pushed through a nozzle into the container. The nozzle may lower close to the bottom at the start of filling and rise as the honey level increases. This bottom-up filling reduces trapped air. Honey flows into the container as a thick amber column, spreading slowly outward. The level rises with a glossy surface. When the target amount is reached, the valve closes. A cutoff mechanism prevents trailing strings of honey. Some nozzles use suck-back action, briefly pulling product upward to stop dripping. This keeps the jar rim clean for sealing. Filled containers move immediately toward capping. Caps are fed from a hopper into a sorting bowl. The sorter orients each cap correctly and sends it down a chute toward the capping heads. For glass jars, metal or plastic lids are placed onto the threads and tightened to a controlled torque. For squeeze bottles, flip-top caps or dispensing closures are applied and tightened. The closure must seal the container without damaging the neck or deforming the cap. Some honey jars receive an induction seal or liner under the cap. In that route, a foil-lined closure passes under an induction sealing head. Electromagnetic energy heats the foil layer and bonds it to the container mouth. The cap remains above it as the outer closure. After capping, the containers pass through inspection. Fill level sensors or check weighers verify the amount of honey. Vision systems inspect cap presence, cap angle, container shape, and visible contamination. Any package outside tolerance is rejected automatically. The exterior of the container may pass through a cleaning station if any residue is detected. Light rinsing, wiping, or air cleaning removes stickiness from the outside surface. Clean containers travel more reliably through labeling equipment. Labeling depends on package shape. Round jars pass through wraparound labelers. A pressure-sensitive label peels from a backing web and attaches to the glass or plastic surface. Rollers spin the jar and press the label smoothly around the curve. Squeeze bottles may receive front and back labels. The bottle is held between belts, while label heads apply each panel. Rollers press the labels flat against the curved or slightly flexible bottle surface. Alignment guides keep the label centered. A coding system marks each package with production data. Inkjet or laser equipment applies a code to the cap, label, jar shoulder, or bottle base. The mark appears as the container moves along the conveyor. For some honey formats, tamper bands are applied around the lid and neck. A sleeve of plastic drops over the closure area. The container moves through a heat tunnel, where hot air shrinks the band tightly around the cap and neck. The band conforms to the package shape as it cools. Croissants reveal their layered structure when a cold butter sheet is locked inside dough and sent through the first laminating rollers. The dough surrounds the butter like an envelope. Its edges are sealed, but the inside is still separate. Dough outside, butter inside. The block moves toward paired rollers that lower with controlled pressure. As the rollers pull it forward, the butter spreads into a thin, continuous layer between sheets of dough. The block stretches longer, flatter, and wider without tearing. This first pass is the beginning of lamination. The croissant does not get its flaky texture from mixing butter into the dough. It gets it from keeping butter and dough in separate layers. Later, when heat enters the oven, water in the butter and dough turns to steam. That steam pushes the layers apart. But before that dramatic lift can happen, the factory has to build the layers with cold precision. The dough begins in an industrial mixer. Flour enters first after sifting. Sugar, salt, yeast, and milk powder or dairy ingredients are dosed in measured amounts. Water is added through temperature-controlled lines. Fat, or a small amount of butter, may enter the dough itself, but the main butter for lamination remains separate. The mixer works the ingredients only to the needed development. Croissant dough needs strength, but it cannot be overworked into a tight mass. It must stretch around butter, pass through rollers, and expand during proofing. The dough becomes smooth, cool, and elastic, with enough structure to hold gas and enough flexibility to fold. After mixing, the dough is divided into large slabs. These slabs pass into a cooling or resting stage. Resting relaxes the gluten so the dough can roll without shrinking back. Cooling firms the dough so it can match the butter texture. If the dough is warm and the butter is cold, the butter breaks into pieces. If the butter is soft and the dough is firm, the butter smears into the dough. Both must meet at nearly the same firmness. The butter is prepared as flat sheets. Blocks of butter or laminating fat pass through a butter sheet former. Rollers compress them into rectangles of even thickness. The sheet must be plastic, not brittle. It has to bend under pressure and spread evenly inside the dough. This hidden sheet is what will later become hundreds of delicate layers. The cool dough slab moves to the lock-in station. A butter sheet is placed on top. The dough folds over the butter from the sides or wraps around it completely. Edges meet and seal, trapping the butter inside. The block now contains alternating material, but only a few layers. The rollers will multiply them. The laminated block enters a sheeter. Rollers reduce its thickness gradually. The dough stretches and the butter stretches with it. The machine does not crush the block in one heavy pass. It reduces thickness step by step, so the butter remains continuous and does not burst through the dough. After the sheet reaches the target length, it folds. A folding device brings one end over the center and the other end over that, or folds the sheet in a book-style pattern. Each fold multiplies the layers. Dough, butter, dough becomes a stack. The stack is turned and sent through the rollers again. This is where the croissant's future texture is quietly being built. Every fold creates more layers. Every roller pass stretches them thinner. The sheet still looks like one pale slab from the outside, but inside it contains repeating bands of dough and butter. The dough rests between folds. Resting keeps the layers from tightening and tearing. The sheet is chilled again, so the butter stays firm. Temperature control is constant. Too much warmth makes the butter melt into the dough, destroying the clean separation. Too much cold makes the sheet crack at the folds. A second rolling pass lengthens the folded slab. The rollers pull it forward with steady pressure. The butter layers become thinner and more numerous. Another fold multiplies the structure again. The sequence may repeat depending on the desired layer count and product style. When lamination is complete, the dough enters final sheeting. This pass brings the laminated dough to the exact thickness needed for cutting. The sheet moves as a long, wide ribbon. It must be even from edge to edge. Thin spots bake too crisp. Thick spots remain heavy. The rollers and side guides maintain a precise width and thickness. Now the shape appears. Cutting wheels slice the laminated sheet into long triangles. The blades move through the layers cleanly. A straight cut gives each piece sharp edges. The triangle shape is essential because it rolls into the curved croissant form. The wide base becomes the center body. The pointed tip wraps around the outside. The triangles may pass under a stretching device. This gently lengthens each piece, so the final croissant has more turns. The stretch must be controlled. Too much pull tears the layers. Too little gives a short, dense roll. Each triangle enters the rolling unit base first. Small belts or mechanical fingers catch the wide edge and roll it toward the point. The dough curls into a spiral. Layer after layer wraps around itself. The pointed tip lands on the outside and must sit underneath or near the base so the croissant does not unroll during proofing and baking. The rolled pieces may be curved slightly. Guide arms bend the ends inward to create the crescent shape. Straight croissants skip this curve and move forward as rolled cylinders with tapered ends. Both shapes depend on the same laminated triangle. The formed croissants are placed onto trays or oven belts with space between them. They are still dense and cool. The yeast has not fully expanded the dough yet. The next stage gives them volume, but it must happen gently. The croissants enter a proofing chamber. Warm, humid air surrounds them. Yeast produces carbon dioxide inside the dough layers. The pieces rise slowly. The spirals loosen slightly. The body becomes taller and softer. Humidity keeps the surface from drying and cracking. Proofing is delicate because the butter layers are still trapped inside. The chamber must be warm enough for yeast activity, but not so warm that the butter melts out before baking. If butter leaks early, the croissant loses lift and becomes greasy. The proofing conditions hold the dough at the edge of expansion without destroying lamination. The proofed croissants leave the chamber larger, softer, and more fragile. Their layers are visible around the edges. The surface may receive an egg wash or glaze before baking. A spray or rotating brush applies a thin coating across the top. This coating helps create a glossy, golden crust in the oven. Now the oven performs the loudest transformation. The croissants enter a tunnel oven or rack oven. Heat strikes the surface first. The butter layers begin melting. Water inside the dough and butter turns to steam. The steam expands between the layers, lifting them apart. The rolled structure inflates from within.